Very excited to introduce Ji Zhang. He's a system scientist at the Robotic Institute at CMU. He's also the founder of Kara. I hope I pronounced that correctly. It's a company that commercializes 3D mapping technologies, leveraging range, vision, and inertial sensing, which are all areas in which Ji has contributed in his research. In more generally, his research interests are very relevant to the symposium and include the robot navigation, perception, Lidar mapping, and computer vision. So this talk is going to be very exciting, and I look forward to it. G, please go ahead.
Thanks for the introduction. We'll talk about exploration today. Not much to say about in the wild, that's to match the name of the symposium, but exploration is our topic of today. So first, I want to say a few words about what robotic exploration means, because this word has been used in our daily life. When we talk about exploration, we are thinking about going somewhere very far. And this process has to do with braveness and loneliness. But when we talk about robotic exploration, it can be exactly the opposite. So like this underground space, it could be right underneath us. It's not anywhere far away, but for some reasons, we don't want to send human operators to go into the space, to explore, to map the space, because there are often some kind of dangers involved. Space can be contaminated, or it involves other types of dangers. So we don't want to risk humans to go into the space. We send autonomously exploring systems into the space to map, to scout, to collect sensor data for us to analyze the space. Okay. So as of today, autonomous exploration is still harder than human operators doing it. By carrying the sensors in a backpack or hold it by hand or mount it to a vehicle to drive it manually through the space, that's still easier as of today. Hopefully that will change. But today, the reason of sending autonomous robots to map and explore spaces is mostly because of the danger. So the problem is a hard problem, especially if we are exploring environments that are very complex, structurally cluttered, shady. So we'll get back to this point of how the problem is difficult. But let's take a look at a realistic civil application as a use case of the technology. So this is the Fukushima nuclear plant in 2011. Disaster happened. Generators flooded in the basement, reactors melted down, and radioactive contamination spread all over the place. So this is a widely used example. The DARPA humanoid challenge uses the example a few years ago. The humanoid challenge was motivated that by the time that the disaster happened, or right before the disaster happened, if there was a humanoid robot to be sent into the basement to close the fuel valves, the disaster could be stopped or largely mitigated. So we are talking about exploration today. We are given a different story. We are looking at this area 10 years after, like today. Over the period of 10 years, the government has spent tremendous amount of effort to rescue this area, to reduce radioactive contamination, to resume farming, and to rebuild the neighborhood. If you look at this whole area, it's getting back to its normal life. But if you look at the nuclear plant itself, there are still these occluded areas completely unknown to the outside world. Nobody knows the situation in there. Nobody knows how to enter the space even. So this is the exact example as a use case that autonomously exploring systems could be sent into the space to scout, to map, and to collect additional sensor data. Okay, so for whatever sensors that we can install on the robot, we can let them carry along by the robot to collect the data from them. And later on, we can embed the data onto the map to get additional information for people to analyze the space, and hopefully that opens the door for somebody to enter the space to start cleaning up the space. Okay, so this is a realistic use case. We are all roboticists. We are eager to do this even today. We want to send these autonomously exploring systems to autonomously map and scout all by themselves. And we're expecting them to come back at some point to bring us the full map of the environment. The realistic, the situation is not that optimistic. Okay, this is the situation of today. If you send these systems to autonomously explore, this is what happens usually. Once it gets in, we cannot go in with them because the space it has some kind of dangers for us to go in. So the systems go in, and shortly after, it loses communications to the outside, because the communications is something that we usually cannot rely on at all time. That's just the way it is. So from there, we don't know what it's doing. It may be still exploring. It may get stuck at some point, but we don't know. We can only hope that it will still come out at some point. And if it does come out, that's great. We have the data. But otherwise, we wait hours after hours. At some point, we say, okay, this is the way it is. Okay, so that's the overall behavior as a system. And we are talking about the exploration problem today. So let's try to look at the problem from a theoretical perspective. Let's try to understand the difficulty of the problem from a theoretical perspective. So first, let me say a few words about the problem modeling, because the problem is discretized. In reality, the vehicle moves continuously through the environment, and today's sensors have a relatively high frequency, usually from 10 hertz to 50 hertz even. So it's almost that the vehicle moves continuously through the environment, and it collects high frame rate sensor data. It constantly scans or perceives the environment. The high frame rate, it's almost that it continuously covers the environment. But to be able to model the problem mathematically, we model the problem with discretized viewpoints. So the vehicle goes to each of these viewpoints, and it takes the sensor data, and it perceives the environment from these discretized viewpoints. Okay, so with that said, the exploration problem is a planning problem. It plans these viewpoints in the environment for the vehicle to go to each of these viewpoints, to take the sensor data and to cover the environment. The combination of the sensor data collected from these viewpoints basically covers the full environment. Okay. So from a systems perspective, there are several tasks that needs to be fulfilled for the system to autonomously explore and to map. So there has to be a representation of the environment that has to be constantly updated through the run for us to keep track of the covered areas, the uncovered areas. The system has to be able to analyze the traversable terrain for ground vehicles. For aerial vehicle, there's no need to analyze the traversable terrain, but there is a need of analyzing the traversable space, because for aerial vehicles, it does not have to care. This part of the terrain is traversable, and this part of the terrain is not. So everything that it sees is an obstacle. But for ground vehicle, it has to actively segment out the traversable terrain from the non-traversable from the non-traversable terrain. So this process is called terrain traversability analysis. So ground vehicle needs terrain traversability analysis. The system needs to be able to estimate the coverage from these viewpoints or to compute the information gain. And from there, it searches this representation for the exploration path. Okay, so this is the whole process happening in the system, in the exploration process. Now, why is this a hard problem? Because there are two steps that needs to happen continuously through the whole course of the exploration. First, this system has to constantly update the representation of the environment to keep track of the covered and uncovered areas. Then it needs to search this representation for a traversable path to guide the vehicle through the environment to fulfill the coverage. And these two steps have to run constantly through the whole course. It's really not that you update the representation and you do one-time search so that you get a path, then you follow this path from the beginning to the end, now the coverage is done. It's really not that case, because the exploration process itself is a recurrent process. Okay, so let me briefly explain this point. The exploration is recursive between covering and to cover more, because as we're talking about exploration, it assumes that the environment is unknown. It does not have any prior about the environment. Upon the system starts, it only sees a small area basically around the sensor, and that's the environment that it knows. And from there, based on that data, it makes a plan to go to cover the environment that it has seen so far, which is a small area. But as it goes, it gradually sees more structures. It gradually figures out more layout of the environment. And from there, it has to constantly update the representation and to constantly replan, to update the path to cover the structure that it has seen so far, because it gradually sees more and more structures and more layout in the environment. So this process has to recur until at some point all the structures in the environment are covered, and that's the end of the exploration. So you see these two steps has to run all the time from the beginning to the end, and it's a time-consuming process, especially if the environment is large scale or structurally complex, cluttered, or over 3D terrain. The problem is particularly hard. Okay. Now, how is the state of the art doing? In general, I can probably summarize: state of the art is not efficient enough in exploration, mainly because of two reasons. So first, a lot of these state-of-the-art methods use greedy strategies. So instead of optimizing the whole exploration path, it's only looking for an instant viewpoint or a few viewpoints, and it connects a short path through these few viewpoints, and it optimizes this short path to do the coverage in the vicinity of the vehicle. So the greedy strategy is ultimately myopic. The symptom with greedy strategy is it often gives us this back and forth motion. Because it's myopic, it does not have a global picture. From the past perspective, what happens is it usually comes to one place to explore, but it cannot explore that area fully. It goes to somewhere else. Then later on, it has to come back to cover more, but even that, it may or may not cover it fully. So it comes here, it goes there, and it comes back and forth. And that reduces the efficiency of the overall exploration. Okay. A lot of the methods don't use an efficient enough data structure. So the problem is a hard problem. It needs excessive processing, but if the data structure itself is not efficient enough, imagine this is an online algorithm. The vehicle has to move continuously in the environment to do the coverage. If it takes 10 seconds for the algorithm to come up with a path, the vehicle has to wait in there for the path to come out. If it takes 1 minute, the vehicle has to wait for probably almost a minute. So a lot of the time, because of the inefficient data structure, the vehicle stops and goes in the environment, and that limits the overall efficiency of the exploration. Okay, So this is a quick overview of the state-of-the-art methods. So here is our exploration framework. We started work from more than a year ago, and the purpose of this framework is basically to push the limit of the efficiency in exploration. So if you look at this framework, this is a hierarchical framework with 2 levels in the data structure. We have first a local area, which is in this big green box, which is what we call the local planning algorithm. The local planning algorithm is an area surrounding the vehicle and it moves along the vehicle. In this local planning algorithm, we maintain the data densely and we compute a detailed exploration path within the local planning algorithm. But out of the local planning algorithm, in the global scale, along this dashed blue line, which is the global path, so that's our global environment. We maintain the data sparsely only in these small green blocks. Okay, so these little green blocks are where the information is stored. So I'll get to this point later in the talk because this is an important representation in our framework. But for now, let's understand the little green blocks are where the information is stored. And the little green blocks basically mean those areas are not fully explored. They need more coverage or more exploration in the future. Okay, so it's kind of putting a mark in the environment to say, okay, well, I have to come back here to explore more at these little green blocks. Okay, so at the global scale, we maintain data sparsely in these little green blocks. We compute a very coarse path through these green blocks, our global path. So the whole insight behind this framework is in the vicinity of the vehicle, close to the vehicle, we need to maintain dense data. We need to compute detailed paths because that's helpful with the navigation. But at the global scale, it's not necessary to maintain the data at that density. We seriously turn down the resolution, use sparse representation, and trade it off for computational efficiency. Okay, so that's the whole insight behind this framework. Now, in the next few slides, I'll briefly talk about the processing at the 2 levels. So here is the processing at the local level, which we call local planning. The local planning is to compute a set of viewpoints and a path through these viewpoints to fulfill sensor coverage around the local planning algorithm. The local planning process is a recursive random sampling process. It's iterative. We sample multiple sets of the viewpoints, and each set, the combination of the viewpoints, fulfill a complete coverage of the structures around the local planning algorithm. Okay, so the algorithm samples a set of viewpoints to make sure there is a full coverage, and it samples more sets of viewpoints. And for each set, it solves the traveling salesman problem to find the tour through these viewpoints. And in the end, it picks the tour that has the shortest path. Okay, so one characteristic in the local planning problem that is worth to mention is there are sensor field of view overlaps in between these viewpoints, because if you look at the structure in the environment, it can be seen by multiple viewpoints. So this characteristic results in what we call the submodularity of the problem. And dealing with the submodularity or the sensor field of view overlap takes a little bit more processing in the local planning process. Okay, the global planning builds a map through the traversable space. As a vehicle moves through the environment, it gradually develops a road map, which is basically a graph. And this graph indicates the traversable space through the global environment. Then on this roadmap, we search the shortest paths in between these little green blocks. Remember, these little green blocks are where the information is stored, and they are the areas that needs more coverage. So we search the shortest path in between every pair of the little green blocks. Then we solve the traveling salesman problem again. At the global scale, to get a tour through these little green blocks, then the local path and the global path are connected on the boundary of the local planning horizon. So that gives us the overall exploration path. Okay, so that's an overview of the technical procedure. Let's use this real example to understand this exploration process a little bit better. So this is real data from aerial vehicle exploring a few buildings on the university campus. So this big green box here is basically the local planning horizon. And these smaller green blocks are where the information is stored. The blue path is the exploration path, obviously. So if we look at this green box, this local planning horizon, we see these little orange dots in a grid pattern. So these little these little yellow dots, not orange dots, these yellow dots are what we call the viewpoint candidates. So we evenly distribute the viewpoint candidates on a grid pattern in the local planning horizon and in the traversable space. Okay. Then when we randomly sample the viewpoints, we randomly pick them from the viewpoint candidates. If you look at these bigger orange dots here along the path, that's the randomly sampled viewpoints. We basically randomly pick them from the viewpoint candidates on the grid. And these selected or sampled viewpoints, or these bigger orange dots, are the sampled viewpoints. Those are the points that the vehicle should go to collect the sensor data, and the combination of the sensor data from these bigger orange dots cover the whole environment. Then from there, we compute a path through these sampled viewpoints. Okay, so let's watch this video. This is aerial vehicle exploring to the right side. The replanning is at 1 Hertz. So every second you see the representation is updated, it's extending to the right side, and the path is replanned to the right side. Okay, so let's watch this process one more time. And this time, let's pay attention to these little green blocks. So we said these little green blocks are where the information is stored. They are the area that needs further exploration, right? So let's see how they are generated. They are actually generated from the local planning horizon. They're left behind. As the vehicle explores, if there are areas along the way that are not fully explored, the algorithm leaves these little green blocks behind, and to remember that it needs to come back at some point to explore more. Okay, so here is another example that I want to show. And while we watch this example, I want to explain an important phenomenon, which is exploration versus relocation. Because if you explore a realistic environment, it often has intersections in it. When you're at an intersection, you can only pick a branch to explore. That's the only way to do it. You have to pick one. And once you go in to explore that branch, and that branch is fully explored, you need to come back to relocate yourself back to the intersection. And from there, you can explore the other branches. Okay, so this video is about that. This area with these little green blocks, that's where the intersection is. Okay, the vehicle is exploring through this branch to here, and that's the dead end. Okay, now we're seeing the vehicle is approaching the dead end. Now that whole branch is fully explored. It's relocating itself back to the intersection. And once it gets to the intersection, it starts to see these orange dots. The orange dots indicates the uncovered surfaces. And from there, the exploration resumes. Okay, so one more time. Right now, the vehicle is exploring to the end of that branch, and it's relocating its back to the intersection, basically getting itself back to these little green blocks. And once it gets there, it starts to see more of these red points, which means that now it sees more uncovered surfaces and it starts the covering process or the exploration process. Okay, now let's see how this phenomenon happens. I need to explain for a few words about what happens in the algorithm, in the processing to make this phenomenon happen. Well, we said the exploration framework is a hierarchical framework. It has the local planning, it has the global planning. In the nominal exploration phase, there are structures that needs to be covered in the local planning algorithm. If you look at these two brown things here, these two brown structures, those are the structures that need to be explored. So the local planning algorithm places these orange dots along the path, and it plans the detailed exploration paths to cover the structures in the local planning algorithm. But once it gets to the dead end, that whole branch is covered. There's nothing more to cover. The local planning algorithm basically degenerates. There is no more viewpoints along the local path. So this local path basically reduces to the shortest path that connects from the vehicle, here from the vehicle to the boundary of the local planning horizon. And from there, it connects to, basically that's the global path. And through the global path, it connects to the next green block, okay? So the local path reduced to the shortest path to the local planning or the boundary, and from there it connects to the next little green block on the global path. Remember we said that the little green blocks they are important in this framework. They mean not fully covered areas, and they need to be covered more. So what happens is the vehicle is basically guided through this path to relocate itself to the next little green block on the global path. And once it gets there, it starts to see more uncovered structures, and the nominal exploration process resumes. Okay. So here are a couple more details about the framework before we look at the results. So one detail is the definition of surface in our system. We define surface as generalized surface. The generalized surface is basically the boundary between free space and non-free space. So if you look at this object, which is this brown structure, when the sensor sees the structure from one direction, it sees the front surface, which is this part on the red line, but there is also an unknown space behind. The unknown space basically means we don't know what's there. It could be occupied, it could be free, but we don't know. Okay, now the definition of the generalized surface includes the boundary between the unknown and the free. Okay, so this part basically is also included as the generalized surface. If you look at the traditional frontier-based exploration, the frontiers are defined as the boundary between unknown space and free space, actually. So basically just these two parts on the two sides, that's used by the traditional frontier-based exploration to explore. Basically, the frontier-based exploration is guided by these two little parts on the two sides, but ours includes this front surface in the front of the object. Okay. Then now based on the definition of the generalized surface, here is our criteria for a surface to be covered. So this coverage criteria, it's unique to us. this criteria is not there in the traditional frontier-based exploration. So this criteria is defined based on our observation that today's sensors can usually see quite far away. If you look at our system, the 3D Lidar in our system can see up to 100 meters, but when it sees from that far, it does not necessarily see well enough. So this criteria is to encourage the system to approach all the structures in the environment to see them well within certain distance and within certain angular range. Okay, so at this point, let me recap on what I said. The exploration process itself is a recurrent process because as the system starts, it only sees the small area, and from there, that small area is enough for it to come up with one plan. And when the vehicle follows the path to explore that small area, it gradually sees more structures in the environment. It sees them, but they're not covered yet. It updates the representation. It replans to approach these structures that have been seen so far to cover them. And along the way of covering these structures, it sees even more structures in the environment. So gradually it sees more, it tries to cover more, and as it tries to cover more, it sees even more. So this is how the recursion happens until at some point, the whole structure, the whole environment is covered and the exploration terminates. Okay, so that's about the technical part. Let's look at some of our results. Here is a result of exploring a large indoor area, starting from a building on CMU campus. It's exploring through another 2 buildings, through connected hallways. So an environment like this is a typical indoor environment. It has mostly long and straight corridors connected through some of the larger dining lobby areas. This has a few typical difficulties or challenges, as in most of the indoor environment, and the challenges have to do with glass and thin structures. So in a few seconds, we will see the whole exploration process, actually right here. This is the whole exploration process, and I want you to pay attention to these little green blocks. These little green blocks are left behind by the vehicle. As it explores, it determines those areas need more exploration, so it marks them down, and later on, it will come back to them to explore more, to clean up these green blocks. Okay, so that's the overall map of the exploration. The whole process has about 8 kilometers of travel over almost 20 minutes. Okay, so here are some comparisons to the state-of-the-art methods. We're comparing to 2 other methods. The one is called MBVP. It means horizontal next best view planner, which is from ETH, and the GBP method is called graph-based path planning for autonomous exploration, and it's from University of Nevada. So the MBVP method uses an RRT data structure in the back. It considers the nodes on the RRT as the viewpoints, and it selects the best branch in the RRT. So while this is said, this is a typical greedy strategy because it's selecting the best branch. The branch only has a few viewpoints on it. So it's greedy and it's myopic. The GBP method is sort of an extension of the MBVP method because the MBVP method has some limitations in dealing with very large environments. Now the GBP method it has 2 levels running side by side at the same time. And it uses heuristics to switch in between these 2 modules. So one module is basically the MBVP method for local exploration, but the other module develops a dense graph through the whole environment for relocating the vehicle. So our framework has a capability of relocating the vehicle. That's not unique to us. The GBP method can also relocate the vehicle. But the way that it does this is to use heuristics to actively switch in between the two modules. The vehicle has to either be exploring or be relocating. It has to be explicitly in either one of them. Now, our framework is made in this way that the relocation process basically is a degenerate case of the nominal exploration. When the local planning problem degenerates, it starts the relocation, and there is no heuristic to actively switch in between modules. Okay, so if you look at this result, ours, which is in blue, covers the whole environment, but the other two miss some areas, like this area, the global map, they're messed by both the other two methods. And if you look at this zoom in picture, and if you look at the green trajectory and the orange trajectory, you see some back and forth motion in there, which limits the efficiency of the exploration. So here is a comparison of the exploration efficiency as the volume explored with respect to time. Because the other two methods didn't explore the whole area, we basically take the amount of volume from their coverage at the end of their run, and we compare to our profile. So even though they can take different paths, the volume can be from different areas in the environment. We basically just compare the volume. That's how we do it. And for the MBVP method, it takes about 1228 seconds to cover the amount of volume that we covered in 206 seconds. And for the GBV method, it takes 1801 seconds to explore the volume that we explore in 550 seconds. So in both cases, we are a couple more times efficient. Okay. Then here is the comparison of the runtime. If you look at the MBVP method, the average runtime for the algorithm to compute a pass is 2.5 seconds. The GBV method is 1.8 seconds. Ours is much faster. It's an order of magnitude faster because we use this efficient data structure in the global scale to seriously turn down the resolution at the global scale and trade it off for computational efficiency. Okay, and that really helps. Okay, here is another result from indoor and outdoor environments. It starts from indoor environment, which is a high bay in our building. Now it's exploring this outdoor space, which is over very 3D terrain. If you know this area, this whole area is on slope. So the vehicle is going to the bottom of that area, and later on it will go up to the top of the area. So an environment like this, it's an interesting environment. It has a big intersection in the middle and a few branches connected to the intersection into different directions. So this is the environment that we can really see how the exploration versus relocation works. So this is the overall exploration process, right? This area where these little green blocks are, that's the intersection area. And a few branches are connected through that area. So right now the vehicle is exploring to the left. Now it's down, it's relocating back to the intersection. Now it's exploring another branch and relocating back. And now it's exploring to the right side. Actually, it's a little fast, but you can see how it relocates itself back and forth, back to the intersection, because there are these little green blocks. It needs to go back there. And once it gets there, it starts exploring again into other branches. Okay. So here is the overall map built through the exploration run. We run online SLAM algorithm to develop the map. There's no post-processing. Overall, the traverse is about 1.4 kilometers at over 20 minutes. Okay. Here is runtime breakdown. We want to look at this local planning time as a whole. Basically, these three columns together. And if we look at the numbers here, these numbers are much larger than the global planning time. Okay. The local planning time together is more than an order of magnitude than the global planning time, because as we said, the data efficient representation as a global scale seriously turns down the resolution and trade it off for computational speed. Okay, so this is a proof of that. The last result is from DARPA Subterranean Challenge. The CMU team is teaming up with University of anyway, the CMU team is attending in the DARPA Subterranean Challenge, and this is the result from the February of last year, which is what we call the urban circuit. It happened in a unused nuclear plant in Washington State, and our system explored that whole floor. If you look at this square, that's where this whole floor is. And this is really a competition run. So nobody is allowed to enter the space. Only robots are allowed to enter the space. And for this particular run, it's fully autonomous. We let it explore all by itself. And it covered this whole environment in 886 meters in 24 minutes. Okay, so a few takeaways before we finish up the talk. Exploration, to our understanding, it's a balance between local coverage and the global relocation to cover more, because the real environment is often convoluted with intersections. It's hard to cover it in one shot. As the vehicle moves along, it covers everything. That is usually not the case. It has to leave these areas behind, and it has to memorize them so that it relocates itself back to cover more in those areas. That's usually where what the reality is. Having an efficient representation of the environment helps, because this whole exploration process has to constantly update the representation, search the representation for the past. Being able to efficiently do these two things, to update the representation and to update the past, helps with the exploration efficiency. Okay, having dense data and detailed paths close to the vehicle, in the vicinity of the vehicle, helps not just for exploration, it helps to almost all the navigation problems. But when it is far from the vehicle, in the global scale, for example, it may not be necessary to maintain the data at that density. There is a possibility to turn down the data density to use a efficient representation and trade off the data density for computational efficiency. Okay, optimizing the full path is always preferred over greedy strategy. In exploration, the greedy strategy often gives us this back and forth motion and redundant revisiting, which limits the efficiency of the exploration. So greedy strategy is myopic. If we can optimize the full path, we always prefer to optimize the full path. Okay, so this is getting to the end of the talk, but before we finish up, I want to briefly introduce our open source website. So our algorithms are being open source, not completely yet. It still takes us a couple more months to open source everything, especially these exploration algorithms. But today, we have this development environment open source, which is an environment for people to develop and to benchmark exploration algorithms. And you can use it for developing full exploration systems as well. Okay, so I'll talk about that. So if you look at this development environment itself is a simulation environment. The idea is you can use these simulation environments. This one is Simucampus, by the way. You can use these simulation environments to develop and to benchmark exploration algorithms in Office, but then you can use the same repository to integrate the system and run it on real robot. Okay, so these are the five challenging simulation environments. Each of them has some challenges, and So we classify the challenges into large-scale convoluted, multi-storage, underlooting terrain, cluttered environments, scene structures, and these 5 environments all have their own difficulties in them. Okay, then this repository has a few basic navigation modules from clear avoidance to terrain analysis. What we're seeing here is the local planner output. The local planner in our system is for clear avoidance. These yellow passes are the clear free passes. And here are the terrain analysis output. Green is traversable, red is not traversable. So, and here are some visualization tools. Okay, so if you look at the system diagram,
hey, G, sorry to interrupt. I'm not seeing the, I'm just seeing your takeaway slide if you're showing a video.
Here. Yeah, same here. I think.
Okay, sorry. Okay, I have to go back to the top then. So here is our open source website. We are still in the process of open sourcing all of the algorithm, but this development environment is there. These are few still need some more time. So here are the environments. There are 5 challenging environments, and here are the challenges that we put in the design of these environments. So this repository has some basic navigation modules. This is local clear avoidance. The yellow passes are the clear free passes going around obstacles. These white points are the obstacles. Terrain analysis output, green is traversable, red is non-traversable. So if you, and it has some visualization tools, okay. So if you look at the system diagram, this repository or this system is basically the mid layer in a full robotic navigation system. You can use it to develop navigation algorithm, especially exploration algorithm, and you can benchmark in simulation. But if you use this repository to integrate full navigation system, this will be the mid layer in the system. It connects to the bottom layer, which is state estimation motor controller, and the upper layer, the top layer, is the high-level planning algorithm. So this is really to help people to develop the high-level planning algorithm. If you don't work on exploration, but you develop other high-level planning algorithms, that's the same. You place it here, and you interface with the mid layer, and the mid layer has all the interfaces to the upper layer and to the bottom layer to take the state estimation and to control the vehicle. Basically, if you send a waypoint to the middle layer, it will take care of it. It will bring the vehicle to that point. Okay. So, but what I want to quickly mention here is another point, because we benchmark in the simulation environment, and while we benchmark, we also ask a person, we ask a human operator to drive through the environment. Okay, so these are the results. This is a human drive through about 10 rounds through the same environment. So this path is not theoretically the best, but almost the best. We really cannot make it better ourselves as human driving. Okay, and if you look at the path, it looks very neat, and you don't feel that you can do much better from there. Okay, the current state-of-the-art algorithms are not doing very well. We don't have to pay too much attention to them, but this is our result, which is still irregular compared to the human result, which is here. It looks much better. And if you look more carefully, it still has some redundant revisiting. Okay, and if you look at the efficiency comparison, the human drive is still much better, especially at the second half. If you look at the first half, our algorithm is doing almost at the same level, or sometimes even better than the human drive. But in the second half, the efficiency drops because it's still not as efficient to use the global picture. And And by the way, it does not have the global picture because it has to explore to gradually figure out the layout. Now the human drive, it's practiced through 10 rounds. It basically knows everything about the environment. So this triggers us to think what we can do further to maximally bring this blue result, this blue curve to the left side to approach this red one, which is the human drive. We won't get exactly there. That's not possible probably, but we want to bring this blue path, this blue curve as much as possible to the left side. And there are some discussions at CMU with Gino, who is the organizer of the workshop. So we are trying to actively leverage experience and prior to predict the uncovered or the unseen areas in the environment. Right now, our algorithm only uses what has seen so far, and it's using it quite efficiently. But for the parts that has not been seen, we don't do anything about it yet. But there is still a chance that you can predict something. It won't be exactly accurate, but it's still helpful. And by doing that, we can probably bring the blue path slightly to the left a little bit. Okay, so that's the end of the talk. Let me share this. Let me share this website, and I can answer questions.
Thank you, G. Do we have any questions?
So I'll share the screen again. Let me send the link.
Okay. We have Sharyar.
Any questions?
Thank you so much for your talk. I have two interrelated questions with your local repositioning when you reposition the robot back. First, when you reposition or back, are you also online replanning to avoid any obstacles? And secondly, how much your solution relies on consistency of your SLAM solution? So if there is some drift while you reposition from one part to another part, there can be some drift, and how much it affects your solution.
Okay, let me answer the second question. I was not exactly clear about the first question, so I need some more explanation. So the second question, how much does it rely on the SLAM? So we have the simulation environments. If you're testing the 5 simulation environments, then there's no effect basically. But in reality, what we have seen is that because we are using the sparse little green block, the sparse representation, that really helps. Because if there is a little bit of drift, the sparse representation basically smooths it out. Okay, so because you don't care about that much details, as long as that whole area is covered, that's fine. You don't have to cover that another time. If you use a traditional frontiers, when you see something slightly shifted, you think that's new structure, and you want to cover it one more time, right? But there is an exception, which is if you go and when you come back, the drift crosses the boundary of the representation. Basically, you drift from one block to another block. So that needs some additional work. From software engineering's perspective, we think it's solvable. Okay, so for your first question, can you explain a little bit more what the question is?
Yeah, so when you're coming back, like you're coming back to one of these green blocks over a long period of time, are you continuously replanning while you're coming back? So for example, if a new obstacle appears, like for example, that was not before when you moved forward, like a dynamic, for example, someone parked a car somewhere in your previous path, will you replan around it, or will you just follow the path that was set before?
Let me show that slide. So here, so basically our replanning phenomenon, our replanning phase, it's basically a degenerate phase of the nominal exploration. So along the way, whenever it sees more structures, this local planning problem reverts back to the nominal healthy phase and it starts to explore again. Okay, so but it's a great question. If you look at the GBP method, they use the heuristics to switch in between. So it's either exploring or it's relocating. While it's relocating, if you if it actually passes some other areas that are not fully explored, it has to ignore them because it's in the relocation phase. It plans a path and it has to get there. And from there, it switches back into the exploration phase. So that method would cause that problem. So even you see some uncovered areas along the way, it misses them and it has to come back later on to cover those areas.
Thank you so much.
Do we have additional questions? I have one, but I'll wait if someone else wants to ask first.
Yeah. So hi G, thanks for the nice talk. So I'm not an expert in exploration. I'm just a little bit curious about this green blocks idea you presented. I think that's very interesting. So this is kind of like the frontier in traditional methods, right? So you know that's unexplored, you mark it down and you come back later. So how does your method, like I would say on a higher level compared to those traditional like depth first search or breadth first search? So I see this green block somehow it looks a little bit like you're doing a breadth first search, right? So can you comment on that?
We are quite different, but okay, let me explore. If you look at the method itself from a systems perspective, it has a front side, it has a back data structure to maintain the data. Now the depth first search or the greedy algorithm to search through this data structure, that's the backside. That's to determine which frontier you go to, right? The front side is the frontiers. So there are differences on each side. The frontiers, that's a dense representation. If you use the traditional way, it's not that it will not mark down. It will still mark down those areas and it will memorize to come back. But as the environment gets large, today's computer has just that much resources. And it's online algorithm, you have to come up with a path fastly enough for it to go. Otherwise, it's stopping there. It's waiting forever. So if you use the dense global representation, it's possible to do it if you have unlimited computational resources, right? But realistically, if you do it like in our method, it uses sparse representation. It's not marking down in those areas with these dense frontier points, but it's using sparse green blocks to mark down in there, which significantly accelerates the processing. So that's the difference.
That's mostly for computational reasons, right? That's mostly for computational reasons because you cannot just process all the data you collect along the way. I think, okay.
Right, that's the first point. Then it gets to the second point. So if you look at the so here, most of these existing methods, they use greedy strategy. Why do they use greedy strategies? People know greedy strategies are myopic. They can only get that far, but why do they still use it? It's not that people cannot understand. Optimizing the whole path is better. Everybody understands it. But in reality, it's a hard problem. If you can use greedy strategy, because greedy strategy, it's greedy and it's faster. So it gets you something. Even you cannot solve the full problem, you can still get something, right? So as long as we can do that, that's good enough in real time onboard the vehicle. So ours is really that we have this efficient data structure that gave us a lot more computational capability, so that from there we can optimize the whole path instead of using greedy strategy to just optimize a little bit, that little bit short path that connects to a few viewpoints. So that's the reason. That's the insight behind the scene. We first have efficient data structure that give us a lot more computational capability. So then we can optimize the full path.
Sounds good. Yeah, I think, thank you. Yeah, I have one small question regarding the local planning. So currently, so not the green blocks, but within the local range, you generate a evenly distributed like grid of candidate viewpoints, and then randomly sample among them, and then plan a path to cover all of these. Right. So I'm curious about, so this assumes you have omnidirectional perception, right? You are using a 360-degree Lidar. So if, for example, you have a limited field of view, like using a depth camera, would that's like randomly sampled procedure be affected? Maybe you need to carefully plan the route, and also you need to plan the orientation of the vehicle to cover as many space as possible. Maybe that's like a extension of future work. I'm just curious.
Right, exactly. It will take more computation for sure, because you're adding 1 degree of freedom, which is the orientation, or a few more actually. So there are ways. So there are ways to accelerate it, because when looking at the surface, you can mostly figure out the norm of the surface, and that helps constrain the orientation.
Yes.
By the way, if you build the system really well, the vehicle may not have to spin for the whole vehicle itself. If you put a gimbal on the vehicle that carries a depth sensor, so that really helps, right? You can keep it spinning all the time. Now it becomes a 360 sensor.
Okay, yeah, that makes a lot of sense. Yeah, thank you. Yeah.
Well, I had one short question, if possible, before we move on. I was very curious about the choice to expand specific the sparse global blocks. How do you choose which one you will expand next? Because it seems like some of them are close by, some of them might be further away, for example.
That's from the global tour. So we have all these little green blocks. We'll compute the shortest path in between every pair of them. Then we solve this TSP, the traveling salesman problem. Which one that is the closest to us on the tour? That's the one that we go to next.
So there is no aspect of heuristically making assumptions about the benefit of expanding a specific node. It's just the shortest path.
Yes. The idea is to cover all of them in the shortest time, not to gain the maximum coverage in the limited amount of time. Right? So we don't care about the instant coverage. Well, while I'm saying we don't care, we are only seeing that little area from the vehicle, because we're not actively predicting the places that are not seen yet. So for what we know about, we want to cover them fully in the shortest time.
Okay.
That's also, you also assume the environment is closed, right? Because you assume the vehicle will come back in a certain amount of time. It cannot be open, right? So that's one of the assumptions of the current implementation.
I'm not sure what open means exactly. It doesn't mean that you don't define an exploration boundary.
Yeah, I guess, yeah.
The whole world.
You don't define a boundary, I guess, yeah. So basically there's a door going to the outdoor, and then
so in our system, we have this boundary. We have this coordinate. It will not explore out of the coordinate.
Okay.
You have to have it. Otherwise it will run out of battery somewhere.
Yeah, exactly. Yeah.
Okay, thank you so much. It was a fascinating talk, and our next session will be chaired by Justin Hart.
Okay, thank you.
Thank you very much. So yeah, hi everyone. We're entering into our last session of papers. I feel like we might as well just jump right into this. Our first paper is the lead author is Wei Xu, which is wonderful. Our presenters are Jixiao Wang and Zifan Zhu. And I'm going to go ahead and get this shared. Let's see, screen to optimize for video, which it's not letting me do that. So that is just life. Share sound. Alrighty.
Justin, can you try again? I think I forgot to make you a co-host. Now you should be able to do the optimize for video thing.
All right. Let me get that set up. Okay, so stop share. Share screen. It doesn't give me the optimized video clip option.
1 sec. I think just some advanced one particular. Oh yeah, I think now you should be able to.
Oh, now I have it. All right.
So one participant has to are allowed to share at one time. I think that's the option you need to do. Yeah.
All right. So does everyone see it? Does everyone see the clip?
Yes.
Yep.
Yes. Hi everyone. I and my collaborator Zizhao Wang we'll be presenting our work, Adaptive Planner Parameter Learning for Mobile Robot Navigation in the Wild. This work was done by Xuesu Xiao, Bo Liu, Garrett Wernell, Zizhao Wang, Zifan Xu, Gaurang Damankar, Annie Nair, and Peter Stone from the University of Texas at Austin, IME Research Laboratory, and Sony AI. This work is motivated by deploying an autonomous navigation system in the wild requires adaptability to a variety of environments by tuning the parameters. So suppose we tune the navigation system in one of the environments, and you want to develop to a different environment that usually requires the tuning of the parameter. So we propose our learning framework, Adaptive Planner Parameter Learning, that learns adaptive planner parameter from different interaction modalities. We propose the following 4 different learning frameworks. For the first one, Apple D, learning from demonstration, and Apple I, learning from intervention, Apple E, learning from evaluative feedback, and finally, Apple R, learning from reinforcement. The first is Apple D. The idea of Apple D is to use the behavior cloning to tune any navigation system. So we model the Apple D as a black box, which takes in the sensory data as an input and generate the motor command to operate the mobile robot. The status of the navigation system is represented by the parameter. So we use the behavior cloning that learns the parameters from a demonstration using the supervised learning. The goal of this optimization is to solve an optimized set of parameters that minimize the loss between the motor command and the motor command generated by the navigation system. And Apple D also deals with the context problem. The human exhibit qualitatively different navigation behaviors in qualitatively different environments. For example, in one demonstration, it usually has a different context that has different navigational behaviors that can be represented by different optimal parameters. So we want to learn the optimal parameter for each of the contexts. So we propose the whole pipeline of the Apple D. First, we collect the demonstration. Then we perform an automatic demonstration segmentation. Then we use a black box optimization to learn a set of optimal parameters for each of the contexts. And finally, we use a supervised learning to train a context predictor. The context predictor takes in the sensory input and predicts the index of the context. Then it uses the corresponding optimal parameters for this context. The evaluation result of this paper can be found in the official website of the symposium.
The next, we introduce Apple I and the input action modality is intervention. So sometimes the full demonstration is not available. And also we found the navigation system with default parameter usually exists 3 kinds of behavior. The green one represents it's working pretty well, and the right one is failures. So sometimes it may get stuck or it collide with obstacles. And sometimes the yellow one is the suboptimal behaviors. For example, in this safe open space, it may still drive very conservatively and drive too slowly. So in this case, for the failure and for the suboptimal behaviors, we could just reset the robot to the beginning and give a short demo of that length. So, and we call that interventions. For all the interventions, we will use the same method in Apple D to learn the parameters for them. However, we cannot expect those intervention contexts will generalize to all environments. So in this time, we augment the context classifier with confidence measure. That is based on the paper evidential deep learning. For example, the context classifier still takes the sensor data as input, and it outputs the prediction probability for each context. Also, it outputs the confidence, and where 1 represents the context classifier is 100% confident about its prediction. So in this time, the confidence is very high. So we believe the prediction is correct, and we will adopt theta1, which is the parameter for context 1. However, in this example, even though the prediction probability is very high, but since the confidence is very low, we will just use the default parameter rather than theta1, because the default parameter is tuned to work for almost every environment, and it should generalize better than this specific parameter theta1. And then it's our work FOE, evaluative feedback. So in some case, the supervisor may not be able to or unwilling to take control of the robot. So we don't have access to either demonstration or interaction. However, in this case, we could still utilize evaluative feedback from human. For example, the human may say good job when the robot is working well, or say bad job when it gets stuck or collide. So in this case, we learn a feedback predictor that takes the standard data and current standard parameters as input, and we try to predict what kind of evaluative feedback that human will give. So once we have this feedback predictor, we'll also learn a parameter policy, where we optimize the performance by trying to select the parameter that will give us the highest probability to receive positive feedback. The whole pipeline is like this. So even though example before we describe a discrete evaluative feedback, but we also accept continuous one, like a score between 0 and 5. So simultaneously, we will train the feedback predictor, and simultaneously we'll train the parameter policy to keep improving the performance of FOE.
Finally, we present Apple R. The idea of the Apple R is to learn a parameter policy from the reinforcement learning algorithm. Because Apple R does not limit to the human's knowledge, but learns completely from its own exploration, so it's supposed to be more generalized to different environments. We first frame our problem as a Markov decision process. The environment is composed by the navigation system and the physical world. At each of the time step, the environment will take in a set of hyperparameters, and the navigation step will navigate based on the parameter for a fixed time step. For example, 2 seconds used in this work, and it will generate the state of the system for the next time step. More specifically, the step is composed of the sensory input, the local goal, and the parameter set from the last time step, which serves as a short memory. And the action is a set of parameters. And the optimization objective is to maximize the accumulative reward. And the Apple R is trained with the twin-delayed deep deterministic policy gradient, which is also called TD3, which is a state-of-art of policy algorithm that deals with the continuous action space. They will also develop the distributed training framework on born dataset. The figure at the bottom shows 3 examples of the born dataset environment with different difficulty level. We have 500 actors on 250 different environments running in parallel to generalize the environment, to generalize the experiences. And then we have one central learner to update the weight of the neural network. And in summary, we proposed the learning framework of the adaptive planar parameter learning. Then we proposed the 4 different learning methods with decreasing level of human interaction. Thanks for listening to the presentation. We're happy to take any questions. Thank you.
Let's go ahead and open up the floor to questions to our speakers. right, well, I have a question. So you have this whole variety of different ways to provide feedback to the robot in order to train it. Have you thought of having like, you know, one single, you have this Apple framework, but have you thought of having sort of an overview training system that could accept all these different inputs? And how would that work?
We're actually developing a cycle of learning framework. I think all of this learning method, it has the capability to take in the previous method, a policy that then could take in any form of input from the human or self-exploration and to improve based on that.
So to add on that, for example, if you have an initial policy that's not working well and you want maybe, or it's good enough, but you want to deploy it into an entirely new environment and then it's performance downgraded. So in this case, maybe you can first collect some demonstration and use FOT to train that. And after that, I think it's basically familiar with the new environment, but still it may struggle at some place, but just a little portion of the space. So in that case, you can use the intervention to correct these behaviors. And or further, if you want to improve, you can use evaluative feedback, which is less demanding because you just need to provide some easy feedback like good job, bad job, like that. So basically, I think you can use this pipeline to, or even if you want to further develop, you have learning multi-policy from Apple D, Apple I, Apple E, and you can use them to bootstrap the learning from reinforcement. To bootstrap the reinforcement learning, so to further learn better policy. Yeah. Any other question?
Yeah, I have one. So have you thought much about the contextual dependency of the learning from the different people and the people's state? And so how you might want to accommodate the fact that, I'm in a rush now, I'm not in a rush now. I mean, of course, you could query a person and get them to classify themselves into state as the kind of lowest bar. And then you learn parameters are contingent on those classifications. Of course, then you have a problem with people not being consistent in how they classify themselves between different people. But so that whole issue of how to deal with different people and the fact that even single individuals have variable, in the real world, different speeds and different levels of urgency and things like that.
Yeah, that's a very good question. So currently our context indeed is just based on the observations. So maybe one thing will help is that in the FOD we have a method that will use Bayesian method to detect different mode of driving behaviors. For example, some people or a single person may be conservative and they drive slowly at this time, but sometimes they may drive aggressively and drive very fast. And the Bayesian method will detect those different modes and split them into different contexts.
Yeah, I think one tricky thing is sometimes people drive slowly because sometimes they drive slowly because they want to drive slowly, and sometimes they drive slowly because they don't feel confident enough or they're bad drivers, right? So then there's two different sort of hidden variables that their demonstrations are contingent on. And knowing which case it is can be hard and maybe interesting.
Yeah, exactly. So we also noticed that in our experiments. So sometimes usually the demonstration will help, but sometimes they are not confident and drive too slowly and it even harms the performance. So maybe after we get all the context and their parameters, we can test them. Maybe for the suboptimal one, we can just don't use them during the deployment. Yeah. Cool.
Thanks.
I have a question. I'm curious to hear your thoughts on how this idea relates to the field of adaptive control. I think in particular, there's a lot of work in like reinforcement learning where I think people are going in another extreme of we want to learn a whole policy, where I think in this work, it's more like we have a policy and we're trying to learn some parameters to tune it. I'm just curious to kind of hear any relationships between things that maybe have gone on in adaptive control in the past versus what you're doing with planning here.
Yeah, that's a good question. So, but so unfortunately, I'm not very familiar with that literature about adaptive control, and I have thought adaptive control is where the model is changing with time, right? Or
potentially,
or
you could have that, yeah. Or you may just not know the model, or you may not know some of the parameters in the model.
Yeah, I guess one thing is here we are learning the parameters for a planner, right? And also from human interactions, right? So I would say so it's very similar to the taste of adaptive control, but I would say it's definitely be opposed to the direction of like reinforced learning, because we do not want to learn an end-to-end motion planner. We want to bootstrap on top of all existing motion planners and just to fine tune the knobs on those classical motion planners to make them better. The idea is because all these advantages of the classical approaches can be inherited, like safety, like assurance, like explainability, all these kind of things. We do not want to learn everything from scratch. We learn on top of that. That's kind of like high level idea why this Apple paradigm can I would say like take the best of both worlds, like classical motion planners advantages, and also give it the flexibility and adaptivity of learning. That's kind of like a high level idea.
Yeah, that makes sense. And I think the way you described it as tuning knobs, like makes that connection to adaptive control even more clear. Where maybe in adaptive control you have some PID knobs that you just don't know what they are, and you want to figure out the best values.
Yeah,
so I think it would be cool, maybe something to explore in the future of how to build that bridge even more.
Yeah, definitely. Yeah, I would say probably from adaptive control, it's more kind of adaptively find those like correct values of those knobs autonomously, right? So we are trying to leverage human interactions, right? Different modality of interactions, because we are talking at field deployment. When you bring the robot to the field, you may not be expert. We as roboticists, we are very good like knob tuners. We can turn the knobs. We have all our knowledge, right? But not for like an end user, like from the general public. They do not know the underlying navigation systems. They do not know how to tune them. But giving them this suite of Apple methods, they can just use their like the interaction modalities of their comfort level. Like some are gamers, they can tally operate like very easily. Some are not willing to take control of the moving robot using the joystick. Maybe just evaluative feedback. Good, bad, very good, very bad. That can also be leveraged in the field.
Well, I hate to cut off a good discussion, but we're slightly behind schedule. So let's jump into our next talk. Our presenters are Sagnik Dakshit and Hiranya Kumar, and I'm going to go ahead and cue up this video.
Hello everyone, my name is Sagnik Dakshit, and today Hiranya Kumar and I am going to present our work on reinforcement learning framework for navigation problems using Lidar scan-based virtual reality. Navigation in the real world is a complex task owing to a number of problems such as large dimensionality, complex rule set, and uncountable number of variations. Research in the same has made significant improvement in training agents to perform automated tasks such as navigation. However, the state-of-the-art methods like reinforcement learning and imitation learning are limited by sample inefficiency and extensive computational resources. The black box nature of such algorithms make it harder for society to accept. Furthermore, the synthetic environments used to train agents is considerably simpler and does not always represent the real world, which affects the deployment performance in the real world, which consequently hinders their widespread acceptance. We propose a framework to facilitate the integration of real-world LiDAR scans with reinforcement learnings algorithms for efficient agent training and testing. We use LiDAR scans to articulately reconstruct real-world scenes in virtual reality. The depth information of the point cloud data is used to identify hazards and traversable paths by thresholding. This is from the motivation that in bird's eye view, buildings and objects have a lower depth value in comparison to traversable paths. With this approach, we convert the 3D scans to 2D grid world. Once the hazards are identified, we mark and allocate reward values taken as user input automatically to all hazards and traversable areas. Motivated by our performance results on tasks constrained over a shorter distance and the intuition that learning to navigate around a city block is easier than navigating around a city with the same rule set, we use hierarchical task setup for testing by breaking down a top-level task into subtasks. This boosts the accuracy by a lot on difficult cases, as we will see later in this presentation. We will explain easy and hard categorization of tasks in the next few slides. Our framework also provides feedback in form of state action pairs, allowing any end user or teleoperator to monitor the autonomous agent. This also allows understanding of scenarios where the agent fails for improvement of the reward structure and overall better training of agents.
Here we are going to discuss the steps involved in generating a 2D reward map from a LiDAR scan. To generate a 2D reward map, we first create a depth map using the depth information from the LiDAR point cloud. The depth map is inverted to facilitate the next step, which is applying a canny edge detector on the depth map to detect significant differences in depth values. This helps us detect traversable paths in the map without the need of manually setting a height threshold for the ground level. After this, we apply a closing morphological operation with a dynamic kernel size dependent on the resolution of the depth map and the final output grid world size, which in this case is 100 by 100. The dynamic kernel size allows us to close up the small gaps between the LiDAR waves close to the source without closing up the gaps produced by the objects. Since the source itself doesn't have any waves going through it, it is represented as a hazard in the final reward map. The image resulting from the closing operation is inverted and downscaled to the required grid size, which is then used by the Unity application as an input. The Unity application goes through the image and creates a map of normal and hazard tiles based on the pixel values. The goal, sub-goal, and start positions are selected randomly from the list of normal tiles, which in this case are indicated by tiles in green. The tiles in red are the hazard tiles. A DFS algorithm ensures that the goal is reachable from the start position by checking if they're connected by normal tiles. For testing, we break down the tasks into easy and hard categories. The difference between these categories is the distance between the start and goal positions. The distance is 4 to 6 tiles for easy tasks and 12 to 15 tiles for hard tasks. The exact distance between the start and goal positions in each episode is randomly selected between these ranges. Since the hazards between the start and goal positions are not accounted for in this heuristic, there are some cases where an easy task can actually be hard to navigate to due to hazards blocking the path. Similarly, there can also be cases where a hard task can actually be easy to navigate to due to a direct hazard-free path being present between the start and goal positions. The algorithm setup decides the input or feedback the agent is provided to make decisions for each step. For this test, we use vector inputs, which includes the difference between the goal and current position of the agent, as well as the types of adjacent tiles surrounding the agent. We measure the performance of the agent in terms of average success rate, which is the percentage of episodes in which the agent was able to reach the goal, and hazards hit, in which is the number of episodes that ended due to the agent hitting a hazard. A low hazards hit number indicates the agent has learned to avoid hazards while navigating, while a high success rate indicates the agent has learned to navigate towards the goal while avoiding any possible hazards in the path. As you can see from this table, with STN disabled, we are able to achieve 84% success rate with 15 hazards hit for easy tasks and 25% success rate with 74 hazards hit for hard tasks. With STN enabled, however, we are able to achieve 98% accuracy with just one hazard hit for hard tasks.
For comparison purposes, we generate synthetic maps with randomized hazards, goals, and starting position of grid size 100 times 100. In this slide, we present results for easy category. In this slide, we present the comparative results for the hard category. As we can see, the agent never manages to navigate to the goal. In this slide, we present our testing results on the Kitty dataset for easy category. The blue grid represents the goal and the white moving grid represents the agent trying to reach the goal. In this slide, we present our results on the hard category without hierarchical testing setup. In this slide, we present our results on the hard category with hierarchical tasks enabled. As we can see from the video, the agent almost always reaches the goal through this hierarchical setup. As future work, we plan to extend the framework to accommodate frontal view navigation as seen in autonomous vehicles and implement strategies to make reinforcement learning training more data efficient. Thank you. And now we will be accepting questions.
All right, well, let's thank our speakers and open the floor to questions. Do we have any questions for our speakers?
I have a minor question regarding one figure in slide 4. So you are trying to generate this grid world using Lidar scans, right? So why is the center of the robot? I know it's not perceived by the Lidar because that's where the Lidar is. You also have the center of the Lidar as red. That's kind of like the danger spot. Can you explain why that?
So since the LiDAR data did not have any data in the 360-degree camera setup, we just gave it as a dangerous spot. I mean, there is no particular reason to making that red. We could make it green as well.
You can just easily make it green because you know that's where the LiDAR is at. That must
Correct.
be safe, right?
Yes, but the LiDAR is again on top of a car, right? Assuming. So the car itself will have some distance front and back. So we didn't want to bump into the car also. So we thought it's safer to give a barrier there.
Okay. Now all these other, so you showed in the video demonstration, all the robot moving. Those are from Kitty dataset.
Yes, the first two were for baseline. In the baseline, we randomly generated hazards, and the others were from the Kitty dataset.
Okay. So what is the training algorithm you're trying to use?
We use the proximal policy optimization.
Okay, gotcha. Thank you.
Yeah, thank you.
Do we have any other questions? So you kind of have this like hand-generated way of pre-processing your map, right? Is there the possibility of plugging in any of the other existing tools out there that output like, a SLAM map or, maybe even point cloud stitching and, watertight surface fitting type things as your pre-process rather than your sort of hand engineered one?
So we tried some automated tools, but since we are doing we are taking the point cloud's depth value to create the hazard map, the pre-processing steps need to be there to get that depth value accurately. Otherwise, if we use existing software, some of them are giving me weird depth values. So in future work, we'll try to automate it, but for now, we have to use this processing steps exactly.
Well, that makes a lot of sense. All right, do we have any other questions for our speakers? Well, our next speaker is Wei Xu, who I think everyone knows at this point. I'm going to go ahead and queue up his presentation.
Hi everyone, my name is Zhishu Xiao. Today I would like to talk about our extended abstract, Safe Learning from Hallucination, or LFH, for navigation in the wild. The motivation for LFH is highly constrained environments where the robot needs to engage in agile maneuvers to squeeze between obstacles. A contrast between a representative normal clustered environments existing mobile robot navigation approaches have addressed versus the highly constrained environment LFH is designed for. Those places will cause trouble for classical motion planners because they will require increased computation. However, learning-based methods do not make things either due to the lack of good quality training data. LFH's inspiration is that robots can comfortably perform a variety of agile maneuvers in open spaces. Those maneuvers in open spaces can be optimal for certain highly constrained environments. By generating, or we call it hallucinating those spaces, we can acquire many training data. Today, I'm going to talk about two hallucination methods. The first method is to hallucinate the most constrained unreachable set. Some notations in motion planning. We are dealing with the configuration space C, composed of obstacles C obstacle and free spaces C free. The robot locates its current configuration CC and wants to go to the goal configuration CG. The robot can take action U at each time step, such as linear and angular velocities. A sequence of actions comprises a motion plan P. A motion planner is basically a function F that maps from obstacle configuration to an optimal motion plan, given current and goal configuration. The motion planning problem is to find that function F. In this LFH, we propose to investigate the inverse function of F. So given an optimal plan P, what is the obstacle configuration C obstacle, which is an easier problem? Unfortunately, this inverse function is not well defined because multiple obstacle sets can map to the same optimal motion plan, as you can see on the right. To address this issue, we introduce the idea of the most constrained unreachable set, C obstacle star. In order for an unreachable set to be the most constrained unreachable set, for any unreachable set that will cause the optimal motion plan P, this unreachable set will belong to the most constrained unreachable set. So basically, the most constrained unreachable set is the obstacle set that contains all other obstacle sets that make the plan optimal. For example, C obstacle 1 and C obstacle 2 both lead to optimal plan P. The union of all these obstacle sets with optimal plan P is C obstacle star. So it is not possible to add even one more single obstacle in the most constrained obstacle set without invalidating the optimal plan P. Then we can train a function approximator, for example, using a neural network to map from the most constrained unreachable set to the optimal plan. The specific instantiation of the most constrained unreachable set can take the form of, for example, Lidar scans or depth images. During deployment, the robot faces the real obstacle configuration, but the robot has only learned how to react to the most constrained spaces during training. This is where we actually utilize the global planner GP in a classical navigation system. The global plan is usually a few rough waypoints the robot should reach in the future, mostly in a lower dimensional workspace, for example, ignoring orientation. We utilize these rough waypoints on the global path to generate a runtime hallucination, and then query our trained G-1 function to produce motion plans during runtime. To deal with uncertainties during deployment, we add Gaussian noise to the produced motion plan and use a forward prediction model to predict where the robot would be after executing the motion. We compute what percentage of the perturbed motion plans will cause a collision, and then adjust the speed correspondingly. We implement the LFH idea on a Jackal ground robot. We first test its performance in the simulated barn dataset with 300 environments randomly generated by cellular automata. As you can see, TWA's traversal time significantly increases with increased difficulty, since it fails to sample feasible motions in the highly constrained workspaces and gets stuck very often. LFH computation is simply creating the runtime hallucination with the global path and then querying a pre-trained neural net, which is not dependent on how constrained the real environment is. We also implemented LFH on a physical Jackal robot. In addition to TWA, we also compared to a state-of-the-art and BC behavior cloning approach and our previous AppleD approach. As you can see, hallucination achieves the shortest average traversal time and the smallest variance. These videos show the LFH performance in natural clustered environments. Remember that the robot does not require any human demonstration for the learning, and it has never even seen a real obstacle during training. But during deployment, it can negotiate through those highly constrained spaces. Note how close the robot is to the obstacles in some frames. These places will require classical sampling-based and optimization-based method, a lot of samples and optimization iterations until it can find a feasible motion plan. But for LFH, the computation is simply constant, and it can maneuver through those challenging spaces without any problem.
Sorry about that, folks. Let me, oh, there we go.
Our second approach is to address the problem that sometimes a global path is not available to generate the runtime hallucination. The inspiration of our second learning from minimal hallucination approach is that in the most constrained obstacle set, not every obstacle is required to make a plan optimal. Therefore, we can identify a minimal enrichable set, randomly sample obstacles in addition to this minimal set during training to generalize for many real-world obstacle configurations, and then deploy without runtime hallucination. We call it hallucinated learning and stillbird deployment, or HLSD. So instead of the most constrained enrichable set, we define a minimal enrichable set. For minimal enrichable set C obstacle min, for any single obstacle configuration C in C obstacle min, removing it from this set will cause a different optimal plan. I will use the point match holonomic robot, which follows the shortest path principle as an example. Let's look at this graphical illustration. Assuming the robot locates at CC and wants to go to CG. Instead of a straight line, which is obviously shortest path, it actually takes a detour through CM. Why is Cccmcg the optimal path instead of the straight line Cccg? It is because of some obstacles. One example obstacle set is shown as the black line. It starts from CM and ends at some point CE. Apparently, it blocks the shortest straight line path Cccg. But you also need to make sure there's no other shorter path than Cccmcg. So on the other side, you will need CE to locate on the ellipse, whose focal points are CC and CG. So CCCG has the same length as CCCMCG per definition of an ellipse. As you can see, if you drop any of the obstacles on the black line, such as this arbitrarily chosen C, CCCMCG are not an optimal path to go from CC to CG anymore. You can actually go through that dropped obstacle C and have a shorter path. So you cannot drop any obstacles on this black line, and therefore it is a minimal enrichable set. Although there are many other minimal enrichable sets as well, we can prove in the paper that the set of all minimal enrichable set is the gray area, composed of a half ellipse and a triangle. So if the gray area is small enough, we can probably just use one representative minimal obstacle set to represent all of them. So let's use the straight line CM prime shown in figure D to represent all of them. CM prime is the symmetrical point of CM with respect to CCCG. To deal with a realistic non-holonomic robot, we apply similar reasoning from the last slide to consecutive configurations collected in open space. The red dotted lines represent the CCCMCG CM prime polygon in the last slide, and we use the black straight lines CM prime to approximate this minimal obstacle set. We call them C obstacle min bar. So these black lines are the configurations which must be obstacles. For other configurations, they can be obstacle or they can be free, as long as they are not within the area where the robot's footprint threads through, defined by the blue boundary. To instantiate the obstacle, we use ray casting for laser range readings. The blue boundary and the black minimal enrichable set give us a minimal and a maximal reading of each beam, showing orange and yellow. And every value between these min and max still makes the red motion plan optimal. Therefore, we can simply sample many times between the min and the max values to generate the many C obstacle as training data. These blue crosses are only one example of a sampled scan. We can also bias the sampling based on uncertainty. For example, for faster motions with higher uncertainty, the sampling can be biased towards the maximal value, while for slower, more accurate motion, we expect the robot to be moving in very confined space and the sampling towards the minimal value. We also implemented HLSD on the Jackal robot. You can find more experiment details in the paper, but the main idea is HLSD can deal with very linear velocities in the training set, such as the 1.0 meter per second data set. But the LFH is confused due to the ambiguity caused by the most constrained enrichable set. Therefore, HLSD does not require runtime hallucination and can also generate fastest navigation performance. A video of HLSD being deployed in a natural environment. We tested the HLSD in the BARM dataset as well. Again, we ordered 300 navigation environments in BARM based on DWA traversal time. HLSD achieved the best traversal time, and the performance is not very sensitive to the environmental difficulty, as shown by the flag green line. LFH 0.4 showing magenta and HLSD 0.4 showing cyan perform similarly, while LFH 1.0 gets confused due to ambiguity, so the red dots are scattered all over the graph. In conclusion, the LFH paradigm investigates the inverse problem of classical motion planning by hallucinating appropriate obstacle configurations to make motion plans optimal. It can generate a lot of safe training data in open space and enables agile deployment in highly constrained ones. One of our future work is to learning hallucination functions instead of handcrafted ones to generalize to different type of robots with higher degree of freedom, such as fast maneuvering drones or even manipulator arms. Thank you for your attention, and I'm open to take any questions.
All right, let's thank our speaker and open the floor to questions. All right, I've got a question. So I see it, you have this paper under review where you're learning about the obstacles, right? So what does that look like? What's the algorithm look like to learn the hallucinated obstacles?
Yeah, so the methods we talked about in this presentation is about manually design those obstacles. For in this learning paper, we try to learn it. The basic idea is we use a encoder-decoder architecture where the decoder is fixed. It is kind of like a differentiable motion planner, like classical motion planner. So we collect lots of training data in the open space, and then we feed that into the encoder. The latent space of the encoded latent space is basically a distribution of obstacles we can sample from. And then we sample from this obstacle distribution. We use this differentiable decoder, like a classical motion planner, and try to reconstruct the same motion plans we collected in open space. In this way, the latent space is constrained to be the reasonable obstacle configurations that make the plan optimal. Then we can sample many times from this latent space to reconstruct many different obstacle configurations, and then train and mapping from obstacle to motion plans this way. Yeah, the idea of this is because we want to extend to higher dimensional workspaces or even like longer planning horizon. We actually show that this method works very well even for 3D flying drone, because that's very difficult for us to design, to manually design a hallucination function to make like a very complicated 3D trajectory from a drone optimal. So through this way, we can learn this embedding space and then try to sample from them, come up with lots of training data without manually designing hallucination function.
That makes sense. Do we have any more questions? Well, if we have no more questions, let's go ahead and proceed to our next presentation. Our presenter will be Saram Siva, and I'll go ahead and cue that up. So let's see now.
Hello, and welcome to our presentation on enhancing ground maneuverability through robot adaptation to complex unstructured off-road terrains. This project was conducted at the Colorado School of Mines in partnership with the United States Army Research Lab. In this research, we addressed the problem of generating consistent robot navigational behaviors for robot terrain adaptation in complex unstructured terrains. The inconsistency in navigational behaviors arises due to the presence of setbacks during robot navigation. These setbacks include reduced tire pressure and wheel slips. This inconsistency negatively affects robots' ground maneuverability and can cause slower traversal times or even errors in robot localization. To address this challenge, we propose a novel formulation for enhancing robot's maneuverability through consistent behavior generation that enables a robot's actual behaviors to match its expected navigational behaviors. Our approach then learns to generate consistent navigational behaviors through learning an offset according to the terrain the robot is traversing on. This offset is then used to compensate for the inconsistency between the robot's actual navigational behaviors and its expected navigational behaviors. Our approach also doesn't require the need to model the various setbacks implicitly. As an experimental contribution, we provide a comprehensive performance evaluation of learning-based terrain adaptation methods by designing a set of live robot navigation scenarios over complex unstructured off-road terrains. Coming to our approach, we first formulate the problem of estimating the robot's expected navigational behaviors using the framework of regularized optimization. Here, the matrix X is used to denote the terrain features, and the matrix Y is the corresponding expected behaviors. The Frobenius loss function is used to encode the error of using a linear model parameterized by matrix W to project the terrain features onto the estimated robot behaviors. Then, the problem of generating consistent navigational behaviors is formulated as a regularized optimization task with the aim of finding optimal matrices W and U that minimizes the objective function in the given equation. Here, the variables y hat represent the actual robot behaviors estimated using a post-estimation technique, such as SLAM. The matrix E is a behavior difference matrix consisting of the difference between the robot's actual navigational behaviors and the robot's expected navigational behaviors. The expected navigational behaviors are provided by an expert human demonstrator while operating on the robot. The first term of our objective function is a Frobenius loss function to model the actual navigational behaviors by considering both terrain features and the behavior differences to achieve consistent navigational behaviors. The second term in our objective is a regularization term named as the feature modality norm. This regularization term enforces sparsity among different feature modalities to identify the most descriptive features for behavior generation. Finally, the last term in our objective is also a regularization term. This regularization term is called the temporal norm and is designed to explore the time steps in historical data that are more important for generating offset behaviors. In our objective function, lambda1 and lambda2 are trade-off hyperparameters to balance the loss function and the regularization term. It's to be noted that the value of lambda1 and lambda2 are always greater than or equal to 0. Our objective function is then able to generate consistent navigational behaviors while identifying the most important feature modalities and also historical time steps. We evaluate and test our approach on a ClearPath Husky UGV robot over complex unstructured off-road terrains. The robot is equipped with an Intel RealSense D435 camera, an Ouster OS164 Lidar, and internal sensors including wheel odometers, inertial measurement units to measure the robot's internal states. The tracks used in our experimentation either show transition between different types of terrain, such as grass to large rocks and grass to medium rocks, or a mix of terrain types in real off-road environments, such as the mixed terrain type 1 and mixed terrain type 2. The mixed terrain type 2 is a forest environment. Our approach is trained on data obtained on simple individual terrains, such as grass only, mud only, or rock only terrains. The training data is obtained as a human operator controls the robot to traverse over these terrains as fast as possible while also maintaining safety, that is, not flipping or crashing the robot. For testing, we execute our approach on each track for 10 runs and record an average for the results. We also test our method against previous learning-based approaches, including learning from demonstration and the state-of-the-art TRAL approach. We compare these approaches over 4 evaluation metrics, including failure rate, traversal time, inconsistency, and jerkiness. Failure rate is taken as the number of times the robot failed to reach its navigational goals from a total of 10 different runs. In the successful runs, the time taken for completing this navigation task is taken as the traversal time. And inconsistency is defined as the measure of difference between robots' expected navigational behaviors and the robot's actual navigational behaviors. Jerkiness is then taken as the average sum of acceleration derivatives along all of the robot's axes. The quantitative experimental results from the table shows that our approach obtains the least failure rate in most of the terrains. Our approach also significantly outperforms the learning from demonstration approach in terms of failure rate. We observe that learning from demonstration method has a lesser traversal time for successful runs, but has a significantly higher failure rate. Moreover, learning from demonstration approach is outperformed with respect to inconsistency and jerkiness metric. Especially, the difference is much more observed in the jerkiness metric. When comparing our approach with the TRAL method, both approaches obtain comparatively smaller values of failure rate over all the terrains. However, when comparing both approaches using performance metrics of traversal time, inconsistency, and jerkiness, the difference between these two approaches is much more visible. We observe that our approach completes the navigation task with lesser traversal time as compared to the TRAL method. Furthermore, our approach also obtains lesser jerkiness measure compared to the TRAL approach. In terms of inconsistency, our approach significantly outperforms the TRAL approach. The clear performance improvement obtained by our approach metric is in view of the fact that our approach is designed to be a closed-loop controller, which considers not only terrain characteristics, but also robot states when adapting the robot's ground maneuvering behaviors over complex unstructured off-road terrains. In summary, we introduced the problem of enhancing robot maneuverability through generating consistent navigational behaviors for terrain adaptation in complex off-road terrains. We then proposed a novel approach for enhancing robots' maneuverability through consistent behavior generation by generating an offset behavior. This offset behaviors enable a robot's actual navigational behavior to match its expected navigational behaviors. Thank you.
All right, let's thank our speaker and open the floor to questions.
Hey, Shrim, very nice presentation. So I'm actually very familiar with this line of work, also your previous TRAL work. So
Yes.
I'm a little curious, like I haven't seen a video demonstration of the final result. I'm very curious to see what is the qualitative difference of all these methods, right? All the numbers like are very convincing, show the advantage of the proposed method. But I'm just curious, what are the qualitative difference, like maybe from a video demonstration point of view?
So the qualitative difference, the main reason, like the TRL approach was just based on data. It was not like on a video demonstration. However, this approach has a video demonstration as it was an extended abstract only for a paper that we have submitted to RSS right now. So the plan was to submit like the video to RSS, like instead of providing the video demonstration. And also the reason is that many of the experiments have also been conducted in like the Army Research Lab facility. And because of that, so we had to build a whole test track, which was like 20 meters by 20 meters long. So look, many of the experimental videos are like shot in there as well. So once the paper is accepted, we plan to release the video demo. And I'll specifically make sure that I have it in my website.
Definitely, yeah. I'm very curious to see the like qualitative difference between them, right?
Yes.
Maybe
Yes.
go ahead, please.
No, go ahead, please ask.
So I'm just, maybe you can, like, I saw there's, for example, for the behavior cloning method, there's 9 failures out of 10 trials, right? So usually the failure is like tipping over or getting stuck on some rocks. Can you like briefly give?
The main failure happens whenever you have a large rock environment, as well as like when you're going through a highly forest environment. In these kind of environments, as there is not much slope, the main failure is just because it gets stuck, or when it navigates just from grass to large rock, during the transition itself it gets stuck. So that's one of the main concerns. So like we use like features which are like global features obtained from like the robot's front camera as well as lidar sensors to like form representations of the terrain and try to navigate. But the main problem comes whenever you have a transition between like one terrain to another terrain. So the robot has to like proactively, that is like before itself, adjust its navigational behaviors. So what happens with learning, like behavior cloning method, is it directly goes into the terrain until a switch comes, right? So when the switch starts to come, the robot then adapts, but by then it's too late. And you see that when there is a transition, it like gets stuck. Flipping over is seen only in 1 or 2 cases, like that I've seen, like when the rocks are too big and the robot is trying to navigate uphill. That's when we see flipping, but it's mostly getting stuck.
Okay, so you're getting stuck, you mean the robot is taking probably like a wrong pass over like a big rock instead of taking a more like smoother pass. Is that the reason of the getting stuck? Or on even lower level, like motor commands, how you turn the wheels getting stuck?
So the robot, so like the behavior cloning method, it's not like a feedback based method. So what it does is it's just like feed forward. So you see the terrain and you try to generate navigational commands. But the problem is, I would say it falls under the domain of not planning the path adequately, because it gets stuck in places where the robot, like the size of the terrain is much higher than the robot's like wheelbase. So it gets stuck in rocks and try to get the wheels rotating, but it doesn't get any traction.
So it it's more kind of like a pass level mistake, I would say, right? You shouldn't go through that big rock. It should be taking a pass beside it, like with smaller rocks. It does.
No, the thing is, with the same rock itself, if you are able to adjust your speed properly, you would not see the robot getting stuck in that rock, right? So what it does is, so if you are just trying to go as fast as possible on these rocks as well, the robot gets stuck. But if you slowly maneuver your speed, we know that we do not want to damage the robot, and we teach the robot in such a way. So when you do that, you would see that the robot is like not getting stuck. So
Yeah, that makes a lot of sense. Yeah, that's also why I'm very looking forward to see the video. How those
yes. So just to add on your question, I know that in the abstract paper we cannot provide all the information, but if you consider like the 4th scenario, which was the mixed terrain 2, it was like a forest environment. The robot often, because we have like an obstacle avoidance also running in the background, so it always considers like tree barks and things like an obstacle. So we do not give like point A to point B. Instead, we do like a waypoint navigation within within each meter, we provide like waypoints for which the robot has to traverse upon.
Okay, so there is a waypoint, like a goal in front of the robot you need to go to, right?
Yes, the robot is going.
In the TRAL work, you do not have a waypoint.
Yes, right? The TRAL. Yes, and right now what we do is we basically have like an external planner which has like point A to point B, and the TRAL approach just acts as a local controller inside of the planner, right? So it's used to just adjust its navigational like velocity, like the linear velocity as well as the steering angle of the robot, right?
Okay, but how did you actually inject the information regarding the waypoint? Is that
so
one part of your state representation, or
like so what we use is the army stack. We already have like the ARL stack, so in that we use like an MPPI planner, like MPPI controller. So it generates like a local planner like for navigating, but what we do is we override the commands which the MPPI planner has given in terms of its linear velocity, and we override it with our local controller. So that's what we are doing. And in terms of states, I don't know if I'm answering this, like if it answers your questions, but the states we use are like just the robots like the twist angles, like the linear and angular velocities. That's the state angles that we use.
So that's the neural work, right? So basically, you're trying to correct the MPPI local planner's linear velocity using this learning method.
Not essentially correct, but override it. So we do not consider, but so just for heading, we use the MPPI as heading, but the local, like just the navigational velocities, I'm using our like TRL approach. Like that's how I override it.
Okay.
Yes, but the video is just because of like we cannot provide like army videos directly.
Yeah. Definitely let me know if when you have the clearance to publicize the video.
Yes, sure. Yeah. Sure.
Thank you.
I think we have time for maybe just one more quick question. Do we have another question? Okay, so I have one that is probably pretty quick. What if you train this on open flat terrain and had that in your data set? Would that change things?
So like yes, I mean if you're only training in like flat terrain, again it needs to be like if you have gravels in flat terrain as well, you need to adjust your robot's velocity when you're training it, right? So we provide like training data from human demonstrators are the ones who teach the robot in this, right? So if you're directly driving it on concrete and grass, it's going to change a lot. But if you try to include like gravels as one of the terrains as well, and like medium-sized rocks, not like really large-sized rocks, you can essentially see the difference. But as you include more and more types of terrains, it's really good just because all the complex environments we see are a combination of all these different types of terrains. So just based on that, so I mean, it is an adaptive approach, which based on feedback from how it is performing during the past few time steps, it tries to generate navigational behaviors in the future time steps. But like to answer your questions, just flat terrains would limit your capabilities. But like I'm assuming this flatness is just in grass and concrete kind of terrains. But if you include like gravels and like medium-sized rocks, that performance you would see in testing as well. Yeah.
Much appreciated. All right. Well, I guess we're coming to the end of our last talk session. Of course, we'll have a discussion and closing remarks after, but this is the last talk of the symposium. And our presenter is Bo Liu from UT Austin. I'm going to go ahead and run that video.
Hello, everyone. Today I'm going to introduce our work, Lifelong Learning for Resource-Constrained Robot Navigation in the Wild. My name is Bo Liu, and this is a joint work with Xuesu Xiao and Peter Stone at the University of Texas at Austin. Speaking of the motivation, ideally we want to design a mobile robot to generalize to unsafe environments, so there is no need for per-environment tuning. And also we wanted to improve from mistakes, so that it won't repeat the same mistakes multiple times. And also, we wanted to store as few data as possible due to the computation and memory constraints. So if we take a look at classical planners and learnable planners, we will see that classical planners are very good at generalization. So a single algorithm can apply to most of the environment. However, whenever a classical planner makes a mistake, it's very hard to improve from that mistake. On the other hand, learnable planners are designed to learn from those mistakes within a single environment, but usually they are very bad, they generalize badly to unsafe environments. So for example, here there is a robot with the classical motion planner navigating in 3 consecutive environments. And we label those parts where the robot navigates less smoothly in red. The robot basically cannot learn from those mistakes, even if we applied it in the 3 environments multiple times. The goal of lifelong navigation is therefore to make a robot that learns across environments with limited memory. And the robot should identify mistakes and learn from them automatically within the environment, and also increase the generalization to new environments while maintaining the knowledge learned from the old ones. In short, a lifelong planner should be good at both generalization and learnability. To this end, we propose the lifelong learning for navigation, the LLFN framework. Basically, it answers what and how to learn. Within a single environment, we want the robot to learn from its own experience. This step we call the self-supervised data collection. Basically, the robot should automatically detect the failures and find the solution. Across environments, we want the robot to do knowledge transfer and essentially the lifelong learning. Here, we adopt the method to constrain the outdate direction to at least not hurt the previously learned knowledge. We will explain in more details later. For the self-supervised data collection part, we design a hand-coded discriminator, D, that takes in a state S and an action A and outputs a score. The score is higher the better. So whenever the D of SA is below some threshold eta, we say a mistake occurs. We use the streaming buffer bstream to keep track of the robot's past trajectory. And if we take a look at a state action pair SA in the bstream such that D of SA is below the threshold, then we look for the most similar state S prime to the state S, such that the action A prime at the state S prime has a higher score above the threshold from the discriminator D. And this S prime A prime is what we want to save and what we want to learn from. We call this positive examples. After we save those positive examples from all of these previous environments in a separate buffer, M1, M2, up to Mk-1, and now we are learning in environment K. In this new environment, we do the following update. Basically, we minimize the loss on the kth environment, subject to that the gradient on the kth environment shares a positive angle with the gradient from the previous environments, evaluated at those positive examples. This is a standard trick called gradient episodic memory from the continual learning community. Next, we see some results from the 3 simulated environments. We provide the overview of those environments on the left, and we label those parts where the robot navigates less smoothly in red. On the right, we provide the average task execution time of the robot evaluated in one environment after training on another. So if we take a look at the second plot on the first row, it evaluates the robot performance in the first environment after training on the second. Here we compare sequential training with LLFN. Sequential training refers to the method that simply sequentially train over those environments without any further consideration. So after training on the first environment, we see that because the robot can learn from its own mistakes, so both sequential training and LLFN achieve the same result. That's the top left plot. However, after learning on the second environment, if we take a look at the second plot on the first row, we see that LLFN is able to keep the performance in the first environment, but sequential training forgets about what it has already learned, and the performance drops drastically. The same pattern continues to the third environment. So here we see that LLFN is able to generalize and also maintain the knowledge from the old environment. Just to summarize, in this work, we propose lifelong learning for navigation that identifies mistakes and learn from them automatically within a single environment, and also increases generalization to new environments and maintains knowledge learned from the old ones. Future works include incorporating dynamic obstacles to the LLFN framework, and also it's possible to design learnable discriminator instead of a hand-coded one. Thank you very much for listening, and we'll provide the QR codes for our full paper and the video of a physical experiment.
Well, thank you, Bo. Let's all thank our speaker and open the floor to questions. Can you tell us a little bit about your plans as it relates to dynamic obstacles? And are you looking at this in the multi-robot case as well?
Yeah, so yeah, because that's also the one review we received from the RAL submission. So people are more interested in dynamic obstacles. So in principle, our method could apply to dynamic obstacles directly, but I can foresee that there are many difficulties. So for example, how do you collect, because in our present work, we are relying on the robot itself to find a solution automatically. But in a more dynamic environment, it might be harder to define what a success move would be. And also from a long-term perspective, for example, if we want to generalize this to multiple robots, then because it depends on what system we are using. It's either like centralized or like decentralized systems. For decentralized systems, it can be very hard because you have to know what the others are doing, because the gradients for the others, and basically you need to know what's the improvement of the other strategies in order to improve yourself. So I think that could be very, very difficult. So maybe our close plan, like most recent plan, will be like just generalize this to a more dynamic obstacle setting and see if that works at all. Yeah.
Yeah, that makes sense. Do we have any more questions for our speaker? Well, I think we had a fantastic set of talks this morning. I'm going to go ahead and turn it over to Zuishu to lead our kind of closing discussions.
Sure. Yeah. Thanks, Justin. Yeah, I think we have a very nice set of talks this morning. So I guess now is the last free discussion session. So feel free to unmute yourself, and if you have any like ideas, suggestions, comments on, I don't know, the whole general case, general idea of applying machine learning for mobile robot navigation in the wild, please feel free to chime in. Yeah, we have covered a lot of different things in these 2.5 days. First day is mostly about navigation in unstructured environment with a focus on outdoor environment, aquatic environment. Lots of nice talks, and also 2 invited speakers in the first day. Second day is mostly a focus on social navigation with other robotic or even human agents. I think, yeah, also lots of interest on that. So today is the full day of extended abstracts. So lots of short papers presented in a shorter period of time, like lots of interesting ideas as well. Yeah, feel free to like any suggestions and any comments, like where should we use machine learning for mobile robot navigation in the wild, and how should we use it, and why should we use it? Yeah, anything, if you have any thoughts. By the way, thank you for sticking around. I know it's a virtual conference. It's kind of difficult to keep people staying till the end. People has other commitments, but that's okay. Like we still have a pretty decent attendance right now. Yeah. Yeah, hopefully we can next time we can meet in person. Yeah, this symposium is supposed to happen in Stanford, which is not possible due to the current pandemic. Yeah. Yeah, if it's a better like situation, we can meet in person. I bet it's gonna be a much better attendance. People can stay to the end, physically stay to the end. Yeah, but I think it's still quite a successful symposium. Like lots of interesting ideas. By the way, everything can be found on the website. The paper presentation, the paper manuscript, and all the industrial partners intro videos, and some of the slides of the industrial spotlight. I think Greg mentioned in the chat that he will be back. I don't know. Yeah, he left for a few seconds, I think.
Yeah. Yeah, he probably had some sort of commitment at noon. Yeah.
Yeah, that's kind of the problem with those virtual conferences, right? People don't really focus on this one thing. They have other commitments at the same time, and they just, they need to take care of different things. Yeah, Michael, I actually have a question for you. So you have done lots of like DRL approach for social navigation. Do you have any other like future plans on this line? So because Harel and I are trying to look into this problem using the hallucination or the deception idea I talked about like during this morning session. So do you have any other like future directions you are trying to pursue on the social navigation end?
Yeah, I was going to ask you about that. You know, how do you hallucinate in a dynamic world?
Yeah. So yeah, I can briefly talk about this. So Herod and I are thinking about, because the idea is, so we are kind of like, I won't say opposed, like the hallucination planner is also end-to-end local planner, but we are still trying to basically leverage as much as possible from the classical work, the classical motion planners, the classical robotics approaches. So hopefully, like, our idea is, if we can avoid learning a local planner to do dynamic obstacle avoidance, that would be great. So because we still, like, when you deploy around, I don't know how the Cato line of work you did like deals with safety. Do you have like a safety check? Like, if you are about to collide to a person, would you stop the robot? Is there anything on that end?
Yeah. We definitely, when we were doing like tests among people, we definitely had safety code in there that was to get within some radius of somebody. Either stop the robot or do something else. And I think that gives you a lot of freedom then to have your robot kind of do whatever it wants when it's not in one of those kind of dangerous states. So I think that sort of state machine infrastructure.
That's the same thing as the LFH.
Just naturally safer.
Yeah. So for the LFH work, we also did a state transition machine. Like whenever you don't feel safe, do some classical stuff. Don't use the learned neural net. So we have two plans to kind of extend this LFH for dynamic obstacles. One is to design like hallucinated obstacles in a high dimensional space, including time. Because currently we are only hallucinating the geometrical location of the obstacles to make the plan optimal, right? The other thing we can do is add the time dimension. So you are actually hallucinating the trajectory of the dynamic obstacles to make your plan optimal. But that could be very difficult because I still don't know how to do it. You need to think about like how do you come up with. So it's actually very related with Chris's talk yesterday, like the braid. Right, it's kind of like the same idea, right? You have like x, y coordinates of the trajectory plus a time dimension. So you want to come up with all these braids to interleave with each other, but not collide, right? That's Chris's take on this. I think there could be a hallucination strategy that on from the same idea, right? Adding this one dimension.
Right. So you're hallucinating right now in position space.
Yeah.
But I'd say a lot of the work in dynamic obstacle navigation is planning in velocity space.
Yeah, exactly.
Something about agents' velocities, and then you figure out what velocity you can choose such that you don't collide with them. So there's all the velocity obstacle, reciprocal velocity obstacle, all those approaches from maybe 10 years ago.
Definitely, yeah.
Maybe that would be a small adjustment you could make. I don't know how small it is, but maybe like one way to attack that problem.
Yeah. And the other thing is, again, like I mentioned yesterday to Chris, like what would be the best cost function? Like what do we really care? Like Chris is entropy and progress, right? And you are probably more about like social norm. How do we add those kind of information in there? That's also difficult. But for the hallucination, it's kind of difficult. How the notion of optimality is much more different. Because for us, for the hallucination work, the current work is mostly about shortest path, like shortest traversal time. That's it. But for social navigation, that's different.
Well, I'm not sure. I think it may still be shortest path or shortest path.
Okay.
I think it's just really hard to quantify what the shortest path in time in a dynamic world because of the interaction between agents. Like if you take a certain path and the other person responds in a certain way, that can influence the amount of time that path is going to take you quite a bit.
Yeah. So what you're saying is,
I was hoping to talk with Chris a little bit more about. I'm going to try and follow up with him, but like understanding. So sure, there's an entropy cost of you want your robot to choose actions that help people understand what the robot's going to do next, so that it like kind of implicitly communicates a topology that you want to pass somebody with. Somehow, I think there's probably a link between that idea of the topological representation and the amount of time that it's going to take to execute that topology. That would be interesting to explore.
Yeah, that should be interesting. Yeah. Okay. Yeah, that's
I do think like most most motion planning problems historically is there's some cost function, like some minimum time. There's something you can see in your horizon. There's something you have to estimate about what you can't predict beyond. And having all of those terms have the same units, if it's all in time, it makes life way easier. It's really hard to balance different objectives that come from totally different units and dimensions.
Definitely, yeah. So in parallel to this idea, the other thing Harel and I trying to pursue here is, can we come up with a runtime hallucination policy that try to mess around with the perception so that we can still use a classical motion planner to do social navigation? So example could be, if you see a person there, somehow you can hallucinate like maybe a bigger region of the person. It's kind of like trying to predict their future trajectory kind of deal, but you are trying to have this RL agent to come up with a, like we also call it deception, right? To deceive the Lidar input so that the end result of this deception, the deceived Lidar can cause a cost map, which is utilized by a classical motion planner to enable very smooth transition between different agents. That's one thing we are currently exploring. Maybe it will work, maybe it not. Yeah, but I guess the action space of the RL agent will be simply like where to add some I don't know, blockage of the moving agent on the other side. And we are particularly interested in narrow hallways. The two person passing each other in a narrow hallway, maybe two robots, maybe one person, one robot. And then how can you, because we have this BW robot in our lab, which navigate around this hallway like for an extended amount of time, like from 9 a.m. to 5 p.m. every day. The thing is, if it sees another robot or it sees another human using I think we are using E-band planner. Using E-band planner, it is very, very likely that the robot will turn around because it thinks, okay, there's an obstacle there. I'm not gonna go this way. It just turns around. So we are trying to come up with the methods that we can increase navigation efficiency. So most of the time it will smoothly pass each other if it's possible, but try not to turn around or get stuck somewhere. That's one thing we are trying to explore right now. Yeah. Harel, you have anything to add?
It's both about hallucinating the location of the object and also the shape of the object. So there's two, like these parameters need to be learned. I mean, we can hand code something, but it's not going to be general. It might be, we might find some function that's general enough, but we're trying to do this by learning the hallucination aspect.
Yeah. So Harel had some previous work on like come up with a strategy, like a polite strategy. One robot go to some place and park, and the other just go through. So it's very efficient for the other one, but the first one, the polite robot, need to stay somewhere. And we try to, I think Harel's previous work is trying to learn where to park so that the transition would be very smooth.
Yeah, and I'll just say about the hallucination that it's not a standalone policy because in some cases, so sometimes the hallway is wide enough to enable two robots to pass, and it's just they occupy the center of the hallway. So if they see each other and one in front of the other, they just see an obstacle and turn around. So if they hallucinate some trajectory of the other robot, they might go through, but the thing is, if the hallway is too narrow, which doesn't allow two robots to pass, then one of them will have to stop somewhere and wait. And that we cannot achieve through hallucination, because if we hallucinate a blockage on the whole entire hallway, the robot would simply turn around. So we still need to use the waypoint method. So if the hallway is wide enough, we'll hallucinate. If it's not wide enough, we'll have to use to learn where to park in order to let the other robot pass.
Yeah, because it's physically infeasible for them to pass in a narrow hallway, right? Yeah, definitely.
Right, and the weight, we can't achieve the weight action through hallucination. That's kind of some limitation of it.
It probably could be a state transition machine, right? Whenever it's not possible to pass, go to the waypoint assignment module. So you park somewhere to let the other one go. Yeah. I also want like to point out that maybe the social norm aspect can be encoded in this hallucination. Because, for example, in a wide hallway, two robots are trying to pass, but if in the middle there's not sufficient clearance for them to pass, and then the hallucination could be always hallucinating on the left, because that's what the social norm indicates, right? People usually go like for the other direction, like we always move on the right, so we hallucinate the opposing robots on the left. That could be somehow encode social norm in this through, for example, like Michael's work on the Cato line. We can say, okay, if the passing is the other way around, that's a penalty. That's not good. And then we can probably try to encourage behaviors that is like in correspondence to social norms using this hallucination agent.
You know, I find it interesting that the iRobot in the presentation, she said that they don't use any machine learning at this point, like on their deployed products.
Yes, yeah, I guess that's
thinking about it, but everything is classical planning right now.
Yeah. That's the thing. So yeah, there's lots of papers on machine learning for navigation, but there's not many product actually being deployed using those learning methods, right?
So what does it mean that you know, either that classical methods work good enough,
yeah,
or that the machine learning approaches are not reliable, or
yes, that's
any resources for their computer. I guess
that's the main thing, right? So like people don't trust machine learning to be deployed in the wild. That's the main thing, right? They trust classical methods. They are verifiable. They have safety guaranteeing. They're also explainable. They can debug. Everything bad happens, they go in there and fix that issue. But for learning, that's usually not the case. Yeah. One thing we like, Bo and I are trying to look at this lifelong navigation is just to trying to identify the weak spot of classical approaches. For example, iRobot like gets stuck in lots of places in your homes all the time, right? Even if it's the same floor plan, it gets stuck the first time. The next time it's come back to this place, it may get stuck again. But this shouldn't be happening because this mistake can be learned. So we can learn from those mistakes. And then in the future, we shouldn't repeat this mistake. I think that's a place where machine learning can really help. Right, so the boss approach is what we try to identify those places. We try to learn an end-to-end local planner to address those. So the next time a similar situation happens, when the classical motion planner gets stuck again, now we switch to the learned local planner. So the benefits of this is super efficient because I think we only use, I don't know how many, like maybe a few thousand data point to learn this complementary, right? So I don't remember its name, but it's super fast, super small amount of data, and also very, very fast to learn. Everything is on board. We don't even need a GPU for this. You know, everything could be on CPU. It's a very small neural net, like 32 neural, 2 or 3 layers. That's it. You know, even use a gradient episodic memory, like it's kind of increased the computation time, but everything is learnable online, on board the robot. Yeah, that's something like we are really thinking. So machine learning, end-to-end learning is probably not like people don't trust it to be deployed in the wild, but really what we can do is find the piece where we can help classical navigation to improve with respect to different experiences, because that's classical methods usually do not do that, right?
I think that in the wild, at least for consumer applications, you're also, even though you're not, you know, putting this on some big GPU, I think you're still a little bit cost constrained. I think you're still a little bit instrumentation constrained. Like they're like, you know, especially from the perspective of a company like iRobot, if you're looking at the total fabrication cost of a consumer product, if I understand the guideline, it's about a third of the MSRP, right? And then you have a company like iRobot that has a bunch of research scientists working there, and people with PhDs, and that only drives your personnel cost up. You know, so the margin per unit needs to be pretty high, right? Which means that you know, if you think of a Roomba going for like maybe $300 and there's like $100 worth of hardware on there, you know, you're now talking about I don't know what type of microcontrollers in there, but it's going to be a teeny tiny thing, you know, and then, you know, I guess the current versions have a camera of some sort on them. So, you know, like I think that I can kind of sympathize with, under that regime, it's pretty difficult to put in, you know, meaningful machine learning algorithm. Plus, they're also usually fielding, you know, when you're fielding a consumer product, you're probably you know, like, not to say they don't innovate, but they're probably fielding the, you know, best known best practices, right? And applying machine learning to this domain, you know, is something that has been done for a long time, but like the more recent stuff, you're never going to see, or rarely will see, put directly to consumer products, right? Unless they feel really like this is the proven thing and this is going to last.
Yeah, I guess it still didn't like. It's not still the benefits brought in by machine learning cannot justify the extra cost, I would say. Yeah, but there's also the other thing I want to point out is this kind of like cloud computing, edge computing, right? So the Roomba in the field at everybody's homes does not need to have all these resources for the training. If they're collecting data and they're connected to Wi-Fi, they can probably just stream all the data online, and then they can do this in their server, and then just downlink all these new learned policies, very small neural networks, to the robots at our homes, and then they can just deploy them without many overhead. I think that's what. So I think I asked Laura that question yesterday. So she was saying, yeah, they are collecting data, but they are currently not doing that, if I understand her correctly. But lots of things are not public; it's confidential. I understand that. But I would say, is learning can definitely be done only in the cloud, you know, and whatever the like front end, the edge computers, the edge robots is doing is only the learned product. The policies, like, just download it from their server and then try to improve their performance in the field. Because and Laura is not here. I hope she's here because I don't want to badmouth iRobot, right? But the case is sometimes it gets stuck in our homes quite often, right? Usually you need to like pick it up, put it somewhere open, and then it resumes. That's okay if it gets stuck, but eventually we want to get rid of this suboptimal behavior, right?
Yeah, I wanted to chime in a little bit about something that was, I forget who said it, but a couple minutes ago, I think interpretability and whether these things can be verified came up. So that's been something I've been looking at a lot in the past year or so, is like, what sort of performance guarantees can we provide for machine learning systems? Because I think it has been the crutch and the easy answer for a long time of, we're going to use classical things because we don't know how to verify machine learning. I feel like there just needs to be more effort in coming up with the tools rather than just saying it's never going to work. So the question comes up though, like, what properties do you even want to verify, and what sorts of guarantees that exist in classical systems actually represent the real world? Because, you know, you could take like a dynamic obstacle avoidance algorithm, say from like 10 years ago. It has some like hard guarantees that if you assume something about other agents in the world, it will avoid them. And sure, you can come up with those guarantees, but the real world, those assumptions about what other agents are going to do in the world probably aren't going to hold. So then you're back in the same boat of, now you have one algorithm that you can maybe explain it well, but the guarantees don't really mean that much in the real world. And then you've got a neural network that maybe performs even better. You can't explain it, but you also can't guarantee anything about it. So I don't know, there's this like question of which of these things are the most important here: explainability, verifiability, performance. And at some point, do we just give up on the explainability and say, if it works, it works? I'm trending in that direction nowadays. And I can also talk a little bit more about the verifiability stuff that we've been doing, if that's interesting to people.
Yeah, but I think I think that the way forward would be to learn within safety guarantees. Like what you said, your robot used to move, but it had some guarantees that wouldn't run into people. The same goes with, you know, autonomous vehicles. We're learning driving policies, but we still have these hard-coded rules of don't go too close to the car you're following and everything. So you're learning within those guarantees. And I don't think that at any time we're going to be able to say, okay, we're putting these aside and we're leaving it all to the machine learning algorithm to figure out, even though we're not sure that it's going to handle. Empirically, it seems to be better, but we're not sure. I don't think anyone's going to drive a car that doesn't guarantee that.
Well, plenty of people driving their Teslas.
That's a good point. Yeah, but again, I'm not sure that they didn't hard code something
right.
to override these dangerous situations.
Right. Yeah, and then another question is, I mean, so I get in, maybe not during COVID, but I'll get in an airplane and I don't know that much about who signed off on it, who guaranteed that it's going to work, but I somehow have some inherent trust in, you know, a person that's going to be a pilot for me, that's going to get me to where I want to get to. I think that gets forgotten about a lot, that people are willing to give up some amount of like uncertainty in whether the system is going to work very well if it provides them a really meaningful service. I don't know.
Yeah, the other thing regarding safety I have in mind is because I had this conversation with Bo a lot. So because for local planning, we think it is pretty good for learning to do, because like when we navigate in a highly constrained space, when we navigate in like tight spaces, we don't actually reason a lot. Like we don't do sampling, we don't do optimization, right? We just react. So that's somewhere it is very suitable for learning because it's reactive, right? We can train a very small neural network to do those local planning for us. So it's very reactive. But on a global level, it's better for very sophisticated reasoning, right? So if you want to go to the airport, which highway you take, which exit you take, which turn do you want to take, all these things can be done by planning, by search, by those like very sophisticated model-based approach. So that's our take on this. So, and then I talked to another professor. We have this argument. He's actually a verification person. He cares about all these things. But he was telling me, hey, if you do everything, if you learn the local planners, it's kind of difficult to verify because it's learning based. We don't trust it. It may collide with obstacles. It may have very like serious consequences because you are learning the raw actions, right? So his idea is we should actually learn the decision making modules on the high level. Right? If all these decision modules are learned, it won't interfere with the low-level safety because the low-level safety are still the classical methods. They can be verified. It's safety. It's explainable. All these benefits from the classical world, right? And that's actually his point. So I saw Genius here. So I had a survey paper on just classical navigation using so basically how people use machine learning for classical navigation problems. Right? There's only one work, I think it's from Gene's group, that's the social navigation. It's trying to learn this high-level global planner or global representation. Not many work are doing those. So you are still using the classical motion planners on the low level, but the high-level decision-making, the global planner is based on the social navigation model. Right, so I think there's two different ideas on this. Where should we actually learn? Should we learn the more reactive local planners, or should we learn the more like sophisticated high-level reasoning modules, decision-making modules? And where does the safety or the guarantees or verification aspects come in? Yeah, maybe you have some ideas on this, Jean?
Yeah, so I'm not sure if I kind of understand the context of the conversation that was going on. But for the safety, I think that it really depends on the problem domain. So we need to consider this risk part. So in the navigation in pedestrian space, even if there is a collision, like the risk is like smaller compared to autonomous driving, like in a highway. So highway is considered maybe an easier setting because it's clean. There are no like people walking around, but they are moving, all the vehicles are moving at a very high speed. So if there is a collision, there will be like a fatal accident. So that risk, because the risk is high, the safety concern is much more an issue. But in pedestrian space, I think because even if there is a collision, we can get away, and probably people may get hurt a little bit, but nothing fatal. So in that regard, maybe people are more concerned about the compliance and is the robot behaving naturally enough to, mingle with the human population. But I guess so that's one aspect, and the other aspect is the explainability. I think Michael was mentioning that, and there was some discussion between explainable system versus competent system. So that's the airplane or other kind of systems that we have this unexplainable trust. Is because we know that the systems work pretty well, and there are accidents, but chance is small. So to that's the chance we are taking. So I think people would much more prefer, I mean, to my personal opinion, would trust more competent system than system that is a little bit unreliable, but it can explain why it went wrong. So there is a trade-off between the two. So that's my personal stake on that.
Yeah, that's a great point. There's a lot of value in seeing something perform well. That gives you some confidence, even if you don't understand why it happened. I think that's a great point.
Yeah, so Jing, what's your reason that you develop social navigation and just utilize all existing local planners? I thought it's for safety. That's what I said, like in the survey. So that's a reason why you are just using classical local planners, but just try to learn a global planner.
Yeah, so for that work, it's more for the general purpose. So there are so socially compliant navigation is one type of behavior, but the navigation behavior can change depending on different contexts. So there is this level of a higher level reasoning going on to detect the context. So if it's a threatening situation, then you forget about the social compliance, you want to be safe. So, so how to do this context switching, that was a more of the reason. And then for the safety part, actually, we added a additional loss term in the navigation training so that it's never guaranteed, but there is a little bit of a notion to avoid a collision. So the comparison to reinforcement learning agents that was actually trained to minimize a collision, it is still a little bit taking a risk, but there is, I think just having that term was the factor that actually ensured the safety in avoiding collisions, because all the data-driven approaches, it's very subtle. So in the training data, there was no collision, so it is less likely to see that kind of behavior during the test time. But it's if we run just a lot of simulation experiments in self-play, we do see a lot of collision actually happening. So there is no objective to avoid possible collision. So even if the learned behavior is implicitly collision avoidance, but there is no understanding of like collision is a bad thing.
But if you are using a classical local planner, then the collision avoidance is taken care of by the classical local planner, right? So then if it's still collides, that's not the learning module's fault. It is the classical local planner is not well enough.
Yeah, it's hard to kind of draw the line, like whose fault that is, because maybe the local planner thought that it would get away or avoid the collision, but maybe there is a localization issue. So there is a low level autonomy that can cause that collision. Also, maybe the global level plan was barely safe. So there is a way to avoid the collision, but with the uncertainty lying in between like perception and localization errors, it can happen. So I think it's a combination of
Okay, so what you're saying is also the global path planned by the global planner is also somehow responsible for the collision because you assign the global goal too close to an obstacle. Maybe that's the reason why it's eventually collide.
Right, because maybe the global planner saw enough pathway so that maybe the local planner will handle going through this narrow cluttered space, but maybe there was too much uncertainty. So there it could have made through, but also there is a high chance, high probability that it might have failed. So. Because it could have routed differently, so to maybe less cluttered, but maybe less optimal looking path, which is safer. But the global planner's decision to let's give it a try on this narrow path, maybe that was the part of the cause.
So I like that way you described it, Gene. We just had a paper that was accepted to RAL and ICRA, and we basically do MPC for a local planner, and we try and learn a policy to select the global sub goal. So you have some global goal maybe 100 meters away, and then the sub goal planner is learning how to place these carrots 10 meters in front of the robot, so that we get these, I say in quotes, guarantees that the MPC is not going to collide with anything. I say that in quotes because I don't really think you can guarantee those things, even if you have hard constraints that you satisfy. But yeah, so basically there's an MPC that plans a trajectory to try and reach that sub goal that's been learned, but then you don't really have to learn the local avoidance part of the problem to try and bring those global and local planning ideas together.
Yeah, this conversation makes me feel like maybe we are too early to complain about the safety issues of learning because MPC still cannot guarantee it, right?
Well, yeah, I think it can guarantee. I think it's just what is it guaranteeing? So if you say, you have to make an assumption of what other agents in the world are going to be doing into the future, and you can avoid colliding with where you think they're going to be according to that assumption, but they may not actually be there, and so then your isn't really that useful.
Also, the assumptions of all the internal components like localization, like all the noise, sensor noise, all these things, right? Yeah. Makes sense.
Yeah, and then as the population becomes dense, a lot of algorithms will fail because there is no feasible solution. So if we really go into a very dense population, then we also need to think about types of actions. Just the mobility, move around, but how to different types of actions so that we can influence the rest of the population. So I need to go there gently, so maybe make a way. So using conversational actions or showing more legible behavior so that people can understand. And so it's kind of implicit coordination. So that's the area that not many existing work have addressed. So there are other types of actions that the robot can actually use, but all these algorithms have been developed in this formulation. There are only like moving actions, and then we kind of only are thinking about the moving part, which is kind of a passive planning idea. So the environment, we will just choose optimal moving actions based on what we have observed. But like, can we actually proactively change these agents because they can also move based on my influence or my suggestions or things like that. So.
Yeah, the other thing I want to mention, in addition to the planning or perception level, is the inclusion of implicit cues. Like we talked a little bit about this, like with Aaron yesterday. So they have, like, Justin has a lot of work on this end as well, right? So because when you interact with different social agents, it's not only a metric or geometric sense, right? It's also in terms of like your body language, your gaze, your motion eligibility. So Aaron has some work on mounting like a physical head and then doing the gaze and the head rotation. So Laura, when Laura was a PhD student with Aaron, she also did some research in this as well, right? Also, I think I forgot her name. Aaron's Marina. Yeah. So she also has some work on this. Yeah. So yeah, I would say eventually we probably also need to explore the other aspect of social navigation, adding those eligibility, gaze, body language, like these things, right? Yeah, Justin has lots of ongoing work on this.
Yeah, I mean, I've set up a set of sort of like parallel lab spaces over here at UT Austin. So I've got a lab in the computer science department where I've set up a virtual reality system. And the reason I've been using VR is because, you know, it's a little bit easier and faster to do experiments than say with like a Vicon. But, you know, there are also very good VR systems that now have integrated eye trackers. And so you can get integrated output. And then you can also get, you know, high fidelity tracks, maybe not at the temporal frequency of Vicon, but, you know, the spatial frequency and the angular frequency. Yeah. And so, or angular resolution. And so that's pretty good. And then you can also create a good virtual environment for your study. So we've got a hallway that we've built in virtual reality with two people passing each other and looking at the exchange of gaze. We've got a paper that was accepted to ICRA. Vaibhav and Helkar, who has been at the symposium, had a paper about like looking at your head angle and looking at, you know, that as a predictive cue for where you're going to walk. We have one where it's gaze as a predictive cue where you're going to walk, same sort of model, just with that. But now we're looking at embedding two people into that environment and then looking at the exchange of body language and also looking at things like torso twist and your shoulders, and are you forecasting what you're about to do and things like that. I think we're probably going to wrap up the forecasting type stuff, where it's like, are you like twisting into a turn and that sort of thing this semester. And then we've got a similar setup where we built a hallway at a cubicle furniture, and we've published a couple papers with like Zweishi was a co-author on a paper where it's a robot with a virtual agent head, and the head is producing a gaze cue, and do people read that cue? And turns out yes, but the gaze cue isn't super realistic. So I've got a parallel group of people working on making better gaze cues. And then, but also looking at the same body language stuff in another uninstrumented setup with Azure Connect cameras and having people actually walking. And then we've got another thing with, it's in conjunction with Peter and Joydeep, looking at the same models, but on the robot, with a camera mounted on the robot with a person tracker, and reacting to the people and what they're doing and reading those cues. And so we're taking all the same data and putting them into neural networks to make predictions. Right now we've got statistical models that show that the predictions are possible, but building regression algorithms so we can put those into planning scenarios. So that's pretty exciting. So that's kind of like, the matrix of what I'm putting together as far as that's all concerned. We'll see how it all goes. So far so good, yeah. But I do think that that's really important because I mean clearly the exchange of implicit communication is, plays a huge role here. And I think that it's like a lot of work has been done on the trajectory along the ground, more so than anything else. So I'm trying to explore a space that's a little bit different and complementary to those techniques. Yeah.
Yeah, definitely. Yeah, I would say that's definitely an orthogonal direction that need to be explored before we actually can have very organically blend like robots, social robots into human crowds to navigate seamlessly. Yeah. Yeah. All right. I guess we are right on time. So yeah, I don't have any like closing remarks. Yeah, basically, thanks everybody for sticking around to the end. And I think it's a successful symposium. Yeah, I hope I wish it's a like physical symposium so we can actually see each other and we can ask the industrial partners to bring in their robots for us to demonstrate their capabilities. But yeah, all the videos are still on the website. Feel free to check it out. And yeah, I think that's it. Yeah, thanks everybody for being here. Thanks for all the co-organizers to spend the effort putting all these together. Yeah, I was to say it's a successful event. And hopefully we open up new conversations to the future, maybe future collaborations. Yeah, Michael, I would love to talk to you about more details, also with Chris, or also with Jean. Yeah, definitely. Like social navigation, I'm also interested in like terrain aware, outdoor navigation, aggressive, like accurate, high-speed navigation in the wild as well. We can definitely keep the conversation open. Hopefully, can form like future collaborations. All right. Yeah. Thank you all, and yeah.
Thank you, Jason.
Thank you.
Thank you for all the hard work. Thanks.
Yeah, thanks.
Yeah, thanks.
Good job.
Good symposium.
Yeah.
See you later.
See you later. Yeah.